Morning, everyone. Good morning, good morning, good morning. Yes. Yeah, right now the temperatures are becoming high every day. The humidity is increasing. Actually, pre-lockdown, so the temperatures was less and humidity was less. But now, after the lockdown, and again as the traffic got increases, the temperatures has been increased. And seriously, a lot of humidity is there. And in some places, yeah. So now is that. Good morning, good morning, good morning. I uploaded the full PDF. Saturday contained whiteboard. Yes, I will be using that. Where is this? What happened today? Yes, yes. I don't know. Okay, fine. Because yesterday we have been discussed about the Houston topic, and we have been. I have explained you how to determine normal stress and shear stress on an element which is subjected to some stress, major principal stress and minor principal stress. And we have been discussed about the major principal plane and minor principal plane, and how to determine the pole point, and what is the radius and all those things. And at the end, we discussed about the pole failure theory, Moore theory, Coulomb's theory, and from that we got to know S is equals to C plus sigma tan phi. Now, my point is, from this point onwards, you see, based on the drainage conditions, if it is an undrained condition, what happens? And if it is a drained condition, what happens? See, yesterday I told you, if it is an undrained condition, undrained means there is no ability or there is no possibility of dissipation of water. So when there is no possibility of dissipation of water, excess pore water pressure cannot be zero and effective stress does not come into existence, then we go for the total stress analysis. And similarly, in the case of the drained condition, the complete dissipation of pore water. So, sir, this undrained and drained you are saying okay, but these drained and undrained conditions depends upon what? Now, Yes. Okay, fine. Okay. So now, again, come to the whiteboard. So as we have been discussed yesterday, the drainage conditions. Now, let me come to the drainage conditions once again. The drainage conditions depends on type of soil and rate of loading. See, we discussed about the drainage and undrained, right? So now you can ask me a question, sir. In reality, where do we see the drainage? Where do you see drained condition? Where do you see undrained condition? When do I use C5? When do I use C dash, phi dash? So now we see that. So the drainage conditions depends upon a type of soil and the rate of loading. So now if you observe, if rate of loading means construction, Nana. Rate of loading means construction is slow and such that water gets time to dissipate. If rate of loading is going to be slow and such that water gets time to dissipate, such a condition is known as drained condition. Such a condition is known as drained condition. Now, so in the case of so if the rate of loading is going to be slow such that the water gets time to dissipate, such a type of condition is known as a drained condition. And similarly, if the rate of loading is going to be quick, if the rate of loading is going to be quick, then does the water gets any time to dissipate? No. So in the case of when rate of loading is going to be quick, if rate of loading is quick, water doesn't get time, water doesn't get time to expel or dissipate. Such a condition is known as undrained condition. Undrained condition. See, as simple as that, what I want to suggest you, what I want to say here is, look, if the rate of loading is going to be slow, if the rate of loading is going to be slow, then water will dissipate because the time is going to be long. But if the rate of loading is going to be quick, immediately the entire pressure will be taken by water. And in order to dissipate the water, it takes some time. Yes or no? So if the rate of loading is going to be quicker, water won't get time to expel or dissipate. Such a condition is known as undrained, which means no dissipation. So this is the points I have been mentioned yesterday. And apart from that, if you look over the type of soil also, for granular soils, generally tests are conducted under drained conditions. So if for granular soils, generally tests are going to be conducted under drained conditions. Why, sir? Sir, in the case of the granular soils, see, I told you the drainage conditions depends upon type of soil and rate of loading. At first I said based upon the rate of loading. Now I'm discussing about the type of the soil mass. So in the case of the granular soils, if in the case of the granular soils, as the permeability of the soil is more, then the water will take less time to dissipate. When the water dissipates, what about the excess pore water pressure? Excess pore water pressure becomes zero immediately. So such type of tests are known as the drained conditions. And now, yes. So now, in the case of clays, you see, in the case of clays, generally the rate of loading is going to be slow. In the case of the clays, as water takes long time to dissipate, generally tests are conducted under undrained conditions. So if in clays, if rate of loading is very slow, in clays, if rate of loading is going to be very slow, then drained tests also can conduct. See, what my point is, at first I told you, in the case of the granular soils, generally the tests are conducted under drained conditions, because in the case of the granular soils, under normal loading or slow loading also, water will dissipate quickly. When the water gets dissipated, such a condition is known as a drainage condition, simple. And in the case of the clay soils, as water does not dissipate quickly, so generally we take it as undrained conditions. Under normal loading, you are going to take it as undrained conditions. But if you apply the load in such a way, it is going to be very slow, then the drained test also can be conducted. Why, sir? Sir, when you make it very slow, then water gets a time to dissipate. Then the test is going to be the drained test. So these are the things that I want to say from the yesterday's class. So I discussed you. Whenever I say drained condition, the analysis is going to be effective stress analysis, and you have to use C dash and phi dash. I hope you have been gone through the yesterday's class also. So I told you, when the rate of loading is slow, then the water gets dissipate. When the water dissipate, effective stress comes into existence, and such a condition is known as a drained condition. Such a condition is known as drained condition. So now, based upon this, stability check. Stability check. Based upon this stability check, the stability check is going to be like, see, in reality or field. In reality or field, you know that shear strength or for stability purpose. What is meant by stability means whether it is going to be safe or not. For stability purpose, shear strength must check under critical conditions. Shear strength must check under critical conditions. Sir, what is meant by critical conditions, sir? Whenever the strength is going to be less. See, do you think the strength is going to be constant? No. As the water dissipates, or if the water is present inside, then there is no effective stress. Yes or no? If water is present inside and excess pore water pressure is there, then there is no effective stress. Then the strength is going to be less. And as the water dissipates, look, in undrained conditions or in drained conditions, in drained conditions are tests. As the pore water dissipates, here the check should be long-term stability check. Long-term stability check. Why? Because in the case of the drain test, as the water dissipates, excess pressure becomes zero and effective stress comes into the existence. It will take some time. So we are going to call it as a long-term stability check. So in the case of drained condition test, we are going to check the soil mass at a long-term stability check. And in undrained condition, so what is the meaning of undrained condition, sir? If a structure constructed on a clay soil, if a structure is going to be constructed on a clay soil, now you see, I told you just now, the undrained conditions are going to be seen in the case of the clay soils, right? So in the case of the clay soil, just now I mentioned in clays, if rate of loading is very slow, then drain. And generally the tests are conducted under undrained conditions because the water won't disappear. So a structure is going to be constructed on clay soil. If a structure is going to be constructed on the clay soil, pore water pressure positive, pore water pressure or excess pore water pressure develops, which means U bar is going to be greater than 0 and effective stress decreases. If a structure constructed on a clay soil, positive excess pore water pressure develops and effective stress decreases immediately after construction. So immediately after the construction, you know that so if a construction is going to be done, or if a if a structure is going to be constructed, so then initially the strength is going to be less. So strength is less, and later on, with respect to time, as water dissipate, effective stress increases and strength gains. See, look, these points we have been discussed in the previous chapters also. Now what I want to say here is, if you construct a structure on a clay soil, or you can take any other earth fill also. In the case of the earth fill, you know that earth fill or earth dam. In the case of the earth dam, in core we have used clay soils or not. So what happens in such type of conditions are going to be like, what happens in such type of conditions are like, you see, at first excess pore water pressure is going to be more, then the strength is going to be less. Yes or no? As the pore water dissipates, if you remember the consolidation, as the pore water dissipates, then the strength is going to be increases. So I told you, for stability purpose, shear strength must check under critical condition. What is the critical condition over here? Can you please tell me, is it a immediate condition or after some time? So immediately after the construction, as our strength is less, immediately after construction, as strength is less, stability check should conduct stability check should conduct immediately after construction. Sir, why you are doing immediately after construction, sir? Sir, immediately after the construction, as a strength is less, sir. Strength less means you have to check whether the structure is going to be safe immediately or not. Because with respect to the time, as pore water dissipates, then what happens? With respect to the time, as pore water is going to be dissipates, then what happens? Strength is going to be increases. So this is going to be short-term stability analysis. In other words, I can write, I don't need to write all these points. So stability should check immediately after construction, because strength is less. See, my point is we have to check. Check means factor of safety, Nana. Check means factor of safety. Immediately after construction, the strength is going to be less. So we have to check the factor of safety immediately after the construction. Such a type of, see, immediately after the construction means we are going to call it as short-term stability check or analysis. Short-term stability check or analysis. So now, similarly, okay. Now let's see. Similarly, if I go for during excavation, again in undrained condition only, again in undrained condition. So what I am going to write is, so during construction of, pavements. So during the construction of the pavements, by removing the self weight of soil, See, what happens over here is, during the construction of pavement, what we do? First of all, we do the excavation by excavation of the soil, by excavation of soil, pore water pressure becomes negative initially or immediately. You see, when you excavate the soil mass, what happens is the particles will lose the strength. So immediately the pore water pressure becomes negative. And now, in the case of the pore water pressure negative, as you know, effective stress is nothing but total stress minus pore water pressure. As you know, effective stress is nothing but total stress minus pore water pressure. So why you are going to do this one? Just wait for a moment, where we are going to discuss about the shear strength characteristics. There you can understand it much more better. So now, during construction of the pavements, by excavation of the soil mass, the pore water pressure becomes negative immediately. When the pore water pressure is going to be negative, you please observe, when the pore water is going to be negative, then the effective stress is more initially. Effective stress is going to be more initially. So during construction of pavements, by excavation of soil, pore water pressure becomes negative immediately. When it is going to be negative, minus of minus, that is going to be positive. Because when pore water pressure becomes negative, effective stress is going to be more. And as time progress, pore water pressure increases from negative to positive, and effective stress decreases. And effective stress decreases results in loss of strength. Results in loss of strength. So when the strength is going to be lost, now you tell me, initially the strength is going to be more. And as a time progress, when the pore water pressure increases from negative to positive, then the effective stress decreases, results in loss of strength. So now here the strength is less, yet long period of time or short period of time? Long period of time. So here strength should stability check should conduct as long-term stability analysis, which means more time. See here, in the case of the undrained, when the positive pore water pressure is going to be developed, then you are going to do the short-term stability analysis. And in the case of the negative pore water pressure, then we are going to do the long-term stability analysis. So in simple words, I can do in undrained condition, if excess pore water pressure is going to be positive and if excess pore water pressure is going to be negative. If excess pore water pressure is going to be positive, generally when the excess pore water pressure is going to be positive, when you apply load, means when you construct a foundation on clay soils, example, construction on foundation on clays, comma, earth dams, comma, earth fills. Pore water pressure becomes negative by excavations. Pore water pressure becomes negative. So in this case, when pore water pressure is going to be positive, then short-term stability analysis, and here long-term stability analysis. So in the case of the undrained condition, now you tell me, so these are the conditions that we are going to do for short-term stability analysis. For short-term stability analysis, which one I have to go for? Total stress analysis or effective stress analysis? So just now I told you, in the case of the short term, you see excess pressure is going to be decreases, means effective stress is going to be decreases. There we go for the total stress analysis. And here we go for the effective stress analysis. You please observe carefully. See, at the last points, you please observe. This is a short term and this is going to be long term. And here is going to be total stress analysis. This is going to be effective stress analysis. It's all depends upon whether the pore water pressure is positive or negative. But in the case of drained conditions, you know that excess pore water pressure is going to be zero. Excess pore water pressure is going to be zero. So when the excess pore water pressure is going to be zero, so then the stability is going to be long-term stability analysis. See here, long-term means after some time. Long-term means once you construct after some time. Short-term means immediately after the construction. So these are the things yesterday we discussed about the drainage conditions. So as it depends upon the rate of loading, if the rate of loading is going to be quick, undrained. Rate of loading is going to be slow, then it is going to be drained. For granular soils, generally we go for drained conditions. In clays, generally tests are conducted under undrained conditions. So this is a stability check. And these are the final points that you need to remember in the case of the undrained condition. See, sir, why the pore water pressure is going to be negative, sir? Sir, you please tell me, sir. Listen, everybody. See, I have given this one. What is the meaning of excess pore water pressure positive? Listen, listen. What is the meaning of excess pore water pressure positive? See, when the pore water pressure is going to be positive, when you apply load, now observe, when you apply load, immediately entire load will be taken by water. Yes or no? Then the excess pressure is going to be increases. Then excess pore water pressure is positive. When you apply the load, similarly, if you remove the load, what happens? Just as simple as that. When you apply the load, inside of the pore, the water will be under compression. As it is incompressible, then the pressure in the water will be increases. Now, if you remove the load, what happens? If you remove the load by excavation, what happens? You please tell me. See, if I remove some load, now I am in. If you apply some load, what happens? Inside of me, the stress would be more. Okay. Now, if you remove the load, then I can be relieved. Relieved means in the voids, whatever the water is there and whatever the pressure in the water will get relieved, means the pressure will decreases. See, when you apply the load, pore water pressure is positive. And when you remove the load, pore water pressure is going to be negative. I hope you understood this. For better understanding, just wait, I am going to give one more thing also. Sir, yesterday you said in under-effective stress is going to be 0, so total stress is used. But today in undrained, that's what Nana I am saying. See, you please observe this one. In the case of undrained, if the pore water pressure is going to be negative, see, this is whether it is going to be short term or long term. That's what you please look over this one. This is a short term stability analysis. This is long-term stability analysis. These are the points. These are the conclusions. These are the conclusions. See, the meaning of this one is long-term means if you wait long-term, you don't know the time. You don't know the meaning. You please observe here this point. Somebody who has asked this me, you please observe this point. If the rate of loading is going to be quick, water doesn't get time to expel. So as water does not get time to expel, then I can say it as an undrained condition. Yes or no? And now in that undrained condition, if I allow the soil mass, means if I allow the water to dissipate, then it is going to be long term. So short term is different and long term is going to be different. So in undrained condition, if pore water pressure is going to be positive, when the load is going to be applied, if pore water pressure is going to be positive, and if the pore water pressure is going to be negative. Pore water pressure positive, then we go for the short-term stability analysis. Pore water pressure negative, then we go for the long-term stability analysis. Please go through these points, then you can understand much more better. So now let's come to the points. What about the magnitude of U? What happens to magnitude of U? Magnitude means, fine. Now, let's see. So why total stress analysis if pore water pressure is positive? Arey Baba, I have given the points over here. You please go through that. If the pore water pressure is going to be develops, if positive, excess pore water pressure is going to be developed, you please go through this point so that you can understand. I wrote initially effective stress decreases immediately after construction, strength is less. So with respect to time as water dissipate, effective stress increases and strength is going to be gains. We need to check when the strength is less. So come on, you tell me, in the case of undrained condition, when the pore water pressure is going to be positive, initially effective stress is less. When initially effective stress is less, then the strength is going to be less. Yes or no? When the strength is going to be less, then stability should check immediately after the construction as the strength is less. Understood? When the pore water pressure is going to be positive. And if you remove the load, then the pressure in the water gets a relief. Relief means reduces and it can becomes negative. So that effective stress is going to be more. As a time progress, the pore water pressure increases from negative to positive and effective stress decreases, results in loss of strength. So stability check should conduct as long-term stability analysis. Why? Because here strength is less, strength decreases yet longer time. See, in this case, strength is less immediately. Here the strength is less immediately. Immediately the strength is going to be less. So stability check should conduct immediately after the construction. And in this case, strength is less with respect to time. So that is the reason why then we have to go for the stability check as a long-term stability analysis. So in undrained condition, it depends upon the pore water pressure. So pore water pressure positive and negative pore water pressure. So these are the points that I can give you. Okay. So now let's come to the next conditions. Please stop. What we do to stability analysis means we need to check whether the dam is going to be safe or not, or whether the structure is going to be safe or not. So for that only. Okay. Now let's come to the yesterday's topic. See, we have been discussed about the Mohr circle and Mohr Coulomb failure envelope. Yes. So if you do remember the Mohr circle and Mohr failure envelope, let's take the same one once again. So please listen to this first and then we can see. Let's come to the soil mass again. Now, let's take this is a soil element. So you know this is a soil element, and whatever the load here, major principal stress, and this one is going to be minor principal stress. And you know when I call it as a major principal stress, why I call it as a minor principal stress? Because the shear stress acting on the horizontal and vertical planes are going to be the zero. So we know this is going to be the major principal stress. This is going to be the minor principal stress. And you take now any plane which is going to make an angle alpha with respect to whom? major principal plane. This is going to be normal stress, and here is going to be shear stress. Yes or no? And if now listen clearly, what is the more failure said? Now let's go back to that. Yes, have a look over here. So more said soil material fails eventually by shear. And Coulomb also take the same thing. And by best fitting, it's a linear function of sigma comma tau f. So the failure stresses are going to be the failure or strength envelope, where C is a cohesion and phi is angle of internal friction. So now this topic, if you observe, this is nothing but the set of the failure stresses. Yes or no? What is meant by failure envelope? What is meant by failure envelope? Locus of the failure stress point. So it is nothing but locus of the failure stress point. Yes. Now let's come over here. Yes. Let's come over here. See if this is the condition, and now you please observe. Let me draw the Mohr circle for this. Yes. Now, here sigma and here it is going to be tau. Here sigma, here is going to be tau. So now, first of all, let me draw a failure envelope. You know the meaning of failure envelope? So let's say this is a failure envelope. You know the meaning of failure envelope is locus of the failure stresses on the failure plane. See, this is a plane Mn R0 and makes an angle alpha. If this plane is going to be a failure plane, if this plane is going to be a failure plane, now you please think, if this plane is going to be a failure plane, then the shear stress will be the failure shear stress. Yes or no? But I am not discussing the failure so far. Please, this is a failure envelope. Now, for this soil mass, you know how to determine the sigma and you know how to determine the tau. And now you draw the sigma 1 and sigma 3. Please, you keep sigma 3 and you keep sigma 1. You draw the Mohr circle. You know how to draw the Mohr circle? You know how to draw the Mohr circle. See, this is a Mohr circle. So let's say yes. Now my question for you is, you please observe, this is a loading condition and here minor principal stress and major principal stress. Everybody have a look. What is the meaning of a failure envelope? What is the meaning of failure envelope? Failure envelope is a locus of failure stresses or not? Yes. Under this loading condition, sigma 1 and sigma 3, the Mohr circle is going to be below the failure envelope. Yes or no? And now, what is the maximum shear stress we can get is nothing but this is the maximum shear stress. I hope you can understand. This is the maximum shear stress. But for the same normal stress, this is going to be the failure shear stress. This is going to be the failure shear stress. Here sigma comma tau f, these points. Because failure envelope, sir, how does the failure envelope is going to be drawn? Wait for a moment. So the failure envelope represents the failure stresses. The failure envelope represents the failure stress, which means for a particular normal stress, the shear stress at failure. Yes or no? So for this sigma 1 and sigma 3, if I draw the Mohr circle, you see over here, the maximum shear stress is less than the failure shear stress, which means whatever the tau maximum you get is still less than fail. Now, everybody, please tell me, does this soil mass is safe or fail or critical? The soil mass is going to be safe. So for 1, in the case of 1, as tau maximum itself is less than tau f, soil is safe. Soil is safe. We can write that. Tau maximum is less than tau f, soil is safe. So now let's see what happens over here. Again, now what I am going to do is I'll increase the normal stress and shear stress. I'll increase the normal stress and shear stress. You please observe over here. So if I increase the normal stress, then what happens? If I increase the normal stress and shear stress, what happens? Think. If you increase the normal stress and shear stress, then the Mohr circle will be enlarged or not, because you know that if sigma 3 increases and sigma 1 increases, then the Mohr circle is going to be increases, because the radius of a Mohr circle is nothing but sigma 1 minus sigma 3 by 2 minus a sigma 1 sigma 1 minus a sigma 3 by 2. Okay, so now see why it is going to be safe is the what is the maximum when the failure occurs. When the failure occurs, the failure occurs when the shear stress is at failure. Yes or no? But here the maximum shear stress itself is less than shear stress at failure, right? Then the soil is going to be safe. Now I am increasing the sigma 1. You increase the magnitude of sigma 1, or by keeping sigma 3 as constant, or you can increase the sigma 3 also. Now what I do is, by increasing the stresses, so now if you observe this condition, okay. So now everybody tell me, everyone have a look. So now I am increasing the stresses. When I increase the stress, see, I am applying the load. When I increase sigma 3 and sigma 1 in such a way, now this is going to be sigma 3 and here it is going to be sigma 1 for this load. Then this Mohr circle will touch us at one point or not. Then the Mohr circle touches at one point. So when the Mohr circle is going to be touches at one point, then whatever the point you see here, that is going to be the failure point. Can I say like that? So if I increase this one sigma 1 and if I increase sigma 3, then at certain plane, forget about the value of alpha, at certain plane, this Mohr circle will touch us the failure envelope. What is mean by Mohr circle? Locus of state of stresses, which means at this point, this is sigma comma tau. And what is mean by failure envelope? Locus of failure stress, because this is nothing but sigma comma tau f. So now for the second state of the soil mass, I am saying if I apply this much normal stress, means major, and this much minor principal stress, then this plane is going to be the failure plane. This plane is going to be the failure plane, and whatever the stress acting on the plane is going to be the failure shear stress. So now what I want to conclude over here is, as long as the Mohr circle is below the failure envelope, As long as the Mohr circle is below the failure envelope, the state of stress is less than failure. So number one, it is going to be safe. And number two, as the Mohr circle touches the failure envelope, as the Mohr circle touches the failure envelope, then the failure shear stress is going to be happen. Number two is as Mohr circle touches failure envelope, soil is in critical state. Soil is in a critical state. Sir, I hope you understood. See, initially I went with some magnitude of sigma 1 and sigma 3, and then I draw the Mohr circle. This Mohr circle is going to be less than the failure envelope, means below the failure envelope. So soil is going to be same. You take any stresses on this Mohr circle, you take any stresses, everywhere the stress is going to be less than the failure stress or not. So now, in the case of the Mohr circle, when the Mohr circle touches the failure envelope, or when failure envelope touches the Mohr circle, at that point the stress is going to be failure. Now, this is going to be at critical condition or not? Yes or no? At a critical condition. This is at the critical condition. Sir, what if you increase the sigma 1 further, sir? What if you increase the sigma 1 further, sir? Sir, if you increase the sigma 1 further, now let's see. Come on, you please tell me. See, this is a state of soil mass at a third condition, and soil is in critical. Okay. Now, you please observe, once the Mohr circle touches the failure envelope, I hope everybody have done the universal testing mission test, UTM, universal testing mission. So in the case of steel and concrete, I hope as you apply the load, the body will undergo compression, and suddenly, once it is going to be failed, what is the stresses? The stress becomes zero or not? Are baba, already for let's say sigma 1 100 kilopascals, sigma C, sigma 3 some 30 kilopascals. So for this one, I am telling you the shear stress is a failure. Now if I increase to 150 kilopascals, then the soil will be collapsed or not? Yes or no? See, if the shear stress is going to be more than shear stress at failure, then the soil will collapse. When the soil will collapse, then the entire stresses are going to be zero. Yes or no? I hope everybody done the UTM test, universal testing mission, for steel bar or for steel rod. When you apply the load, slowly the stresses are going to be increases. Once the steel gets fails, what is the stress? Zero. Once the failure attains, then the soil will crush or not? Once the failure occurs, then soil will crush, then entire stresses are going to become zero. This type of condition is not going to be possible. This type of condition is not going to be possible. So I'll write some conclusion points over here. So means just for the sake of understanding this one, now I'll write the conclusion points. So have a look. Conclusions are: number one, when Mohr circle is below failure envelope. When more circle is going to be below failure envelope, soil is safe. Soil is safe. And when more circle intersects failure envelope, soil is in critical state. Soil is in critical state. And third one, more circle above envelope, more circle above envelope is not possible. Literally, they are not going to be possible. So when more circle is below failure envelope, soil is safe. When more circle exactly intersects at failure envelope, soil is going to be critical. So just now I said to you why it is going to be critical, because now I hope you understood the conditions over here. So when I increase the sigma 1 and sigma 3, so that when the more circle is going to be intersects the more circle gets intersects the failure envelope, this point is going to be the failure point. Mind it, that point is going to be the failure point. So more circle above the failure envelope is not going to be possible because state of stresses are 0. I can write as once soil fails, the state of stresses are going to be 0, which means there is no state of stress. More circle represents the state of stresses. So for a given normal stress, what is the shear stress? That's what the more circle represent or not. And what about the failure envelope? For a given normal stress, what is the failure shear stress? So as long as the more circle is going to be below failure envelope, for a given normal stress on the more circle, the shear stress, on the failure envelope, the failure stress. As long as tau becomes less than tau f, then the soil is going to be safe. Yes. So now tau is equals to tau f. And so now let's see this critical condition only. Sir, how major stress increases by applying the load? Yes. Critical means, what is the meaning of critical? What is the meaning of critical? About to fail or not? The meaning of critical is going to be about to fail or up to critical, no failure. If you go just beyond the critical, then there is a failure. So at a critical condition, the stress, that is a failure stress. For example, soil is going to be fail at 50, which means up to 50 it is safe. And if you increase beyond 50, then definitely the soil is going to be completely failed. So now let me take the second condition only. I have explained the 3 state of the more circles, 1, 2, 3. One is more circle below failure envelope, soil is safe. And now the critical state, let's see the critical state. Now see the critical state. So if you look over the critical state, yes, let me draw that again. So this is sigma and here it is going to be tau. Now let's draw the Mohr circle. So this is a Mohr circle. So for a given set of stress sigma 3 and sigma 1, this is a Mohr circle. Now when the failure envelope touches, then the soil is going to be critical state or not. That's what I mentioned. So let's see. Now, if you observe, whenever the failure envelope touches at one point, so whatever I have drawn is nothing but the failure envelope. Whenever the failure envelope, whenever the failure envelope touches at one point, this is known as failure envelope. This is known as failure envelope. So whenever the failure envelope touches at one point, that point is going to be the critical point, because you know that, see, for that normal stress and for the shear stress, if this is a failure plane, then what is this angle? Then alpha becomes alpha f, tau becomes tau f. So now my point is, Are sir, how come you say this is going to be failure plane, sir? What is the angle made by the failure plane, sir? Sir, you know that whatever the failure envelope, the angle of the failure envelope is going to be phi. Yes or no? Yesterday we discussed about the angle of failure envelope is going to be phi, and the intercept, this intercept is going to be c. So this angle is going to be phi. If this is phi, here also it is going to be phi. So now, whatever this point is going to be a failure point. So let's take the same figure once again over here, please. So now, observe. Yeah. So see, if this is the sigma 3 and if this is sigma 1, this is going to be the failure plane. Now, you know what is this point? This point is going to be pole. Yes or no? Through the pole, have you remembered yesterday's class? Through the pole, any plane should pass through the pole, because you know this is major and this is minor. What is this point? Pole point. So now, if I draw a line through the pole point, if I draw a line through the pole point, now this is known as failure plane. You please go through that once again. So let me show you one more time, please. Let me show you that. Yesterday we discussed about the Mohr circle, right? Now Everybody please focus over here. See, I told you this is a Mohr circle, right? Yes. If this is a plane, Mn is nothing but a plane. What is mean by Mn means? Mn just I am giving you some plane, Mn. So through the pole, if I draw a plane making an angle, what is the angle over here? Alpha. See the same plane. Now if I take this plane as a failure plane. Now, this is going to be the failure plane, will touch us at some point or not, sigma comma tau f. Sigma comma tau f. What is the angle over here? Alpha. So now, if you look over here, so just the same thing, but instead of Mn now as a normal plane, I'm going to take it as a failure plane. Then this is going to be failure plane. See, this is failure envelope and this is going to be failure plane. Don't think failure plane and failure envelope both are same. So now, whatever the point where it is going to be give, this gives a set of stresses. This gives a set of failure stresses, sigma comma tau f. Now, whatever the angle, you know, this is nothing but major principal plane. I have discussed this one yesterday, major principal plane. So now, you know, this angle is going to be alpha f. Why? Because the angle made by any plane is going to be alpha, and if it is going to be failure plane, alpha becomes alpha f. So now, from the properties of the circle, if this is the center, you know it clearly. Again, now you see this is going to be the center. So you know that if it is going to be alpha f with respect to center, that is going to be 2 alpha f. With respect to center, that is going to be 2 alpha f. And mind it, whatever the angle over here is nothing but 90 degrees. See, this is nothing but perpendicular, right? 90 degrees. So now, from the properties of circle, we can take this as a 2 alpha f, where alpha f is angle made by failure plane with respect to major principal plane. Angle made by failure plane with respect to major principal plane. See, I took this one and I told you when Mohr circle intersects the failure envelope, soil is in the critical state because the state of the Mohr circle is tau. And when it touches the failure envelope, the tau becomes tau f. Whenever the tau becomes tau f, then the plane is going to be failure plane. The meaning of the failure plane is on that plane the soil is going to be about to fail. On that plane the soil is going to be about to fail. So for a given loading condition sigma 1 and sigma 3, and if it is going to be failure plane, then my question for you is, what is the angle made by the failure plane, which is nothing but alpha f. So now everybody, you please look over here. From the figure, can I write O? Let's take it as A and let's take it as a B. Please listen. So from the figure, from triangle OAB, if you observe carefully from the triangle OAB, now this is going to be 5, this is going to be 90. Then what about this angle? This angle is going to be, what about this angle? Everybody have a look. 5 and this is going to be 90. Then what about this angle? 90 minus alpha f. And 90 minus alpha f is equals to, see, if this is 2 alpha f, then what should be this angle? If this is 2 alpha f, then what should be this angle? 180 minus 2 alpha f. Yes. this is 5 and this is going to be 90. This is going to be 90 minus 5. So 90 minus 5 is equals to, if this is 2 alpha f, then the other angle is going to be 180 minus 2 alpha f. You know the complementary angles principle. 90 minus 5 is equals to 180 minus 2 alpha f. So now here, if you go with this one, then what happens over here is, okay, 180 minus 2 alpha f, then 2 alpha f is equals to 90 plus 5. You please look over here. 2 alpha f, 180 minus 90, 90 plus 5. Then what is alpha f? Alpha f is equals to 45 plus 5 by 2. This is very important bit in the case of the previous GATE and IAS examinations. See, whatever the points I discussed today, if you go through the previous GATE, in previous IAS, then you can get down every point. So this is very important. What is alpha f? Alpha f means angle made by the failure plane with respect to major principal plane. So what is mean by failure plane? This is locus of or set of failure stress. And what is mean by failure plane? Plane or line on which failure occur. This is known as a failure plane and is known as failure envelope. And what is the angle of the failure envelope? The angle of the failure envelope is going to be phi. What is the angle of the failure plane? Alpha f. So what is the relation between the failure plane and the failure envelope? Failure envelope slope is going to be phi and failure plane is going to be 45 degrees. Yes, sir, why you discussed all these things, sir? Now, this is the conclusions I am going to say. I hope you understood the concept behind it. So earlier I discussed about Mohr circle for set of stresses, and then I discussed about the failure envelope, and then now I have joined the failure envelope. This failure envelope is nothing but a tangent to the Mohr circle. Then the failure is going to be happen. And yet a failure or at a critical condition, what is the angle made by the failure plane alpha f? This is 45 plus 5 by 2. So now from the given, you know that alpha f is equals to 45 plus 5 by 2. Okay, fine. Now observe clearly condition. If phi is equals to 0 degrees, failure envelope is a horizontal. Yes or no? If phi is equals to 0 degrees, failure envelope is going to be horizontal. See, now, what is the meaning of failure envelope? The slope. Phi is nothing but angle of the failure envelope. You know, phi, angle of failure envelope. Alpha f, angle of failure plane. So now, if this is the case, if phi is equals to 0, failure envelope is a horizontal. So then what is the meaning of this one, sir? Failure envelope is going to be horizontal. So this is the meaning of failure envelope is going to be horizontal. So whenever the failure envelope is going to be horizontal, what is the phi value? 0 degrees, which is going to be exactly parallel to the x-axis. And now this is going to be sigma and this is going to be tau. So if phi is equals to 0, if friction angle is going to be 0, failure envelope is going to be horizontal. In the case of pure clays, I told you earlier, in pure clays, the strength is due to cohesion, not due to friction. So when phi is equals to 0, if I draw the Mohr circle, then this is going to be the Mohr circle. Yes. Yeah. So if this is the Mohr circle, now can you please tell me where is the failure point? This is the failure point. Yes or no? Wherever Mohr circle or wherever the failure envelope touches the Mohr circle, then the point is going to be the failure point. So now at this point, whatever the failure stress, this nothing but tau f is nothing but tau maximum. I hope you understood the meaning over here. When the failure envelope is going to be horizontal, means when phi is equals to 0 degrees, then the tau becomes a tau f, and the tau f is nothing but the tau maximum. So the failure shear stress is nothing but the maximum shear stress. And now if this is going to be the pole point, you know, this is nothing but the pole point. Any plane that passes from the pole, to the failure point. So now you know that this is going to be the failure envelope. This is failure envelope, and this is going to be the failure plane. So whatever the stress, failure stress, sigma comma tau f. So what is this tau f? Tau f is nothing but tau maximum, and this angle is going to be 45 degrees. Sir, why, sir? You please see, sir, what is this value, sir? This value and this value are representation of the whom? Slope. Then what is alpha, sir? 45 degrees. So alpha f is 45 degrees. And what I want to say here is, this is very, very important. So when phi is equals to 0, failure envelope is horizontal, then the failure shear stress is going to be tau maximum. Now similarly, if phi is greater than 0 degrees, if phi is greater than 0 degrees. Now let's see what happens if phi is going to be greater than 0 degrees. So whatever the expression I have made so far, that is nothing but the phi greater than 0 degrees only. So again, so now you see here phi is going to be greater than 0 degrees. Yes, which means there is a phi value. So when there is a phi value, so now if there is a phi value, if I draw the Mohr circle, yes. So now if you see here, in this case, see, in the case of the sands, pure sands, in the case of the pure sands, phi is greater than 0. Yes or no? In the case of the C5 soils, C5 means cohesion is there, friction is there, which means it's a mixture of coarse grain and fine grain soils. So now phi is equals to 0. So when phi greater than 0. Now when phi greater than 0, you please look over here. This is the failure point. Yes or no? Sigma comma tau f. And this is nothing but the failure stress. But what is the maximum stress? This is the maximum stress. This is going to be the maximum stress. So now this is a failure shear stress, and this is going to be tau maximum. So can you please tell me now, does this one is going to be same as the earlier one? No. So in this case, you please observe, whatever this line, now this line is going to be the failure line. Yes. You don't need to write those. You can directly say that. So now this line is going to be the failure plane or failure line, and this is going to be the alpha f. Whatever this value, this is going to be tau f. So when phi greater than 0 degrees, then tau f is going to be less than tau maximum. Then tau f is going to be less than tau maximum. So here, what I want to conclude you over here is the failure shear stress. You please observe, look over this one. When phi is going to be greater than 0 degrees centigrade, which means phi is going to be present over there. When phi is going to be present, then the failure envelope alpha f is going to be more than 45 degrees. Alpha f more than 45 degrees. You please go through this one once again. So when phi 0, alpha f is exactly 45 and tau f is going to be tau maximum. Because you know, when alpha becomes 45 degrees, you know that yesterday we discussed, have we discussed or not? If alpha is 45 degrees, then the shear stress is maximum shear stress or not? Now if I am saying alpha f is also 45, alpha 45 tau maximum, alpha f 45 tau f, both are same. So when phi 0, then the failure shear stress is equals to maximum shear stress. When phi greater than 0, then the failure shear stress is less than the maximum shear stress. So now the conclusion over here after all this discussion is the conclusion. Tau f can be less than or equals to phi can be greater than or equals to 0 and tau f can be less than or equals to tau maximum. So there was one previous ESC question. They have given the question as consider the following statements. Consider the following statements and state which of the following statements are going to be true. Now, failure shear stress, always failure shear stress is equals to maximum shear stress. When does the failure shear stress tau f becomes tau maximum? When the phi is equals to 0 degrees, then only tau f becomes tau maximum. And now, when does the failure shear stress is going to be? Statement number 1, I mentioned you. Failure shear stress, always failure shear stress tau f is less than the tau maximum. No, it is not going to be always. Second one, always the failure shear stress is equals to maximum shear stress. No. Third statement, always failure shear stress is more than tau maximum. No. Now the fourth one is the failure shear stress can be less than or equals to tau maximum. The failure shear stress can be or less than or equals to tau maximum. So this is the conclusion, final conclusion I want to mention. So with this, see all these are, see in this chapter there are a lot of conceptual bits are going to be there. If you go through the previous ESC, see same like a consolidation chapter. That's the reason why still I did not discuss that test. I was looking over the more circles and pole points. I'm just revolving around the major principal stress, minor principal stress, failure plane, alpha, alpha f, phi, and the pole points only, so that you can try to connect all those points at the same time. Remember, phi is 0, it's not origin. When c is 0, it's going to be origin. What is the meaning of phi? Phi means slope, right? What is the meaning of phi? And what about this one? This is nothing but c, right? So now coming to the next topic. See, it's not the end. I have explained you first one what alpha f, and from the alpha f I have given these conclusions. Now From figure, again, triangle OAB, go back over here. So now let's see again. You know, from the origin to the center, this value is going to be sigma 1 plus sigma 3 by 2. From the center to the origin, this value is going to be sigma 1 plus sigma 3 by 2. Now you see this portion. Let's take this as a x. Now can I write from this portion tan phi is equals to c by x, and can I write x is equals to c cot phi? So now this value is going to be c cot phi, because you see tan phi, I am extending the failure envelope. Phi is equals to tan phi is equals to c by, this is going to be the x portion. So this is going to be the x portion. So now I can write this x as a c cot phi. Okay. So obviously this is going to be c cot phi. Now from the triangle OAB, so let's represent again over here from the triangle OAB. Okay, so the same figure I am drawing over here. Yes. So now this is O and here it is going to be AB. The same thing, whatever I represent over here, I am drawing again. So that what about this angle? This is phi and this is 90 degrees. So this is going to be 90 degrees. And whatever this value I have given you, this value is going to be c cot phi plus sigma 1 plus sigma 3 by 2. So if you have any doubt, you please go through that. From the triangle OAB, I don't need to write, but give me a minute, please. Yeah. So now from this triangle OAB, then can I write sine phi? You please observe sine phi. See whatever this total value, what is this total value? Sigma c cot phi and sigma 1 plus sigma 3 by 2. And what about this value AB? This is radius, right? What is radius? Sigma 1 minus sigma 3 by 2. So from that, this is going to be c cot phi plus sigma 1 plus sigma 3 by 2, and this is going to be radius sigma 1 minus sigma 3 by 2. And you know that sine phi is equals to what is a phi? AB, opposite by hypotenuse. See, don't think OA is a hypotenuse. Now OB is going to be the hypotenuse because these are 90 degrees, right? If this is opposite, this is going to be the adjacent. So now you please substitute this condition over here. So what is AB? AB means sigma 1 minus sigma 3 by 2 by c cot phi plus sigma 1 plus sigma 3 by 2. So now you take this to the other side. If you take to the other side, then sigma 1 minus sigma 3 by 2 is equals to sigma 1 plus sigma 3 by 2 sine phi plus c cot phi, right? What is meant by cot? Cos by sine. Sine gets cancelled. C cos phi. And sigma 1 minus sigma 3 is equals to sigma 1 plus sigma 3 sine phi plus 2c cos phi. Because you please take that 2 to the other side, then you please convert the sigma 3 to the other side and sigma 1 to the here. See, look, sigma 1 into sine phi, sigma 1 into sine phi, take to the LHS, then I can write sigma 1 minus sine phi is equals to sigma 3, 1 plus sine phi plus 2c cos phi, 2c cos phi. And now from here, sigma 1 is equals to sigma 3 into 1 plus sine phi by 1 minus sine phi by 2c cos phi by 1 minus sine phi. I hope you have understood this condition. See, from the sine phi, I am taking this condition because I am going to use this one later also. So, because see, though it is going to be, I am still in the basic, but I am telling you, this condition is going to be helpful for us n number of times. You will observe. You'll appreciate this later. So now, this condition from this one by rearranging see, already I have given this equation, right? Sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f. See, whatever this equation, this is going to be tan square alpha f plus 2c tan alpha f. Yes. So sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f. Now this condition is known as plastic equilibrium condition. Plastic equilibrium condition, where you know that alpha f is nothing but 45 plus 5 by 2. At 45 plus 5 by 2. See, what is the tan square alpha f, sir? Why you have written tan square alpha f, sir? Sir, the meaning of the tan square alpha f is, you know, from trigonometry, tan square 45 plus 5 by 2 is nothing but 1 minus sine phi by 1 plus sine phi. So this equation is known as plastic equilibrium equation. See, so far I have been given two equations. One is S is equals to C plus sigma tan phi yesterday, and now I got one more relation. What is the relation between the major principal stresses and the shear strength parameters? What is the relation between the major principal stresses and the shear strength parameters? So sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f. Sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f. So now that's all from this condition. So this is a critical state, yet a critical state. So I have explained a lot of things regarding to this. At a critical state, this is going to be the Mohr circle, and failure envelope touches the Mohr circle as a tangent. So from this, we got alpha f as 45 plus 5 by 2. And from there, if phi is equals to 0, then tau f is equals to be tau maximum. And alpha f is equals to 45. And this equation is going to be sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f. Yes, this is 1 plus sine phi by 1 minus sine phi. I'm sorry, 1 plus sine phi by 1 minus sine phi. Yeah, yes, the tan square 45 plus 5 by 2 is 1 plus sine phi by 1 minus sine phi. Okay, so I hope you got the equations now. What does this equation say, sir? This equation says about how the failure is going to be happen and how these stresses are going to be seen. Finally, this equation is going to be, you observe what are the conditions you are going to hear: the major principal stress, minor principal stress, alpha F and C. So now, ultimately, whatever the stresses you have been applied, this is on a soil mass, and this soil mass will have C and phi. So at the failure point, how you are going to determine the C and phi. So now let's go for the next one. Yes, look, this is the details given. So why you have discussed all these things? Now let's take types of failure envelopes. Types of failure envelopes. So the types of failure envelopes are: number one, cohesionless soils. Yeah, now you will be understand this. You please observe cohesionless soils. What is the meaning of cohesionless soils? Pure sand, which means cohesion is equals to 0. See, in the case of the cohesionless soils of pure sand, C is equals to 0. Now, if I draw the failure envelope, look, if I draw the failure envelope, so now the failure envelope is going to be passes through exactly origin. So the failure envelope is going to be passes through origin. So now you see here, in the case of cohesionless soils, when C is equals to 0, the only parameter is going to be phi. Now, how to find out the phi? So somebody asks, what is the usage of this equation, right? Now I am going to tell you. Look, if they give you the, if they give you this, understand much more. So now, if you observe over here, if this is a soil mass and if this is a soil mass, so now I applied sigma 1 and I applied sigma 3, there is a failure. So this soil mass, from this, for this soil mass, what is the equation I got? Sigma 1 is equal to sigma 3 tan square alpha f plus 2c tan alpha f. So now you please look over here. I can write, yes, sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f. So then c becomes 0. When c becomes 0, then sigma 1 is equals to sigma 3 tan square alpha f. So then from this one, I can write alpha f is nothing but tan inverse of square root of sigma 1 by sigma 3. Alpha f is equals to tan inverse of square root of sigma 1 minus sigma 3. Yes or no? See, is this entire process is really required for you? Is this entire process is going to be really required for you? See, in the case of the pure sand, C is going to be 0 and phi is going to be greater than 0 degrees. Yes. So now I want phi. The logic is from Mohr circle. If I know the Mohr circle, there comes the logics. These are the logics that you need to look over. So now the logic is, yes. Have a look. So this is the angle we require, and this is going to be sigma 3 and this is going to be sigma 1. So now, as usual, this is a failure plane. Just now I mentioned, you see, with respect to center. So let's take OAB. And you know that from this, the angle phi is nothing but whatever this value, please tell me, please. This is sigma 1 plus sigma 3 by 2. And this is radius, which is nothing but sigma 1 minus sigma 3 by 2. So from Mohr circle, in triangle OAB, sin phi is equals to OAB by OB, which means sigma 1 minus sigma 3 by 2 by sigma 1 plus sigma 3 by 2. Sigma 1 minus sigma 3 by 2 by sigma 1 plus sigma 3 by 2. So from this, I can write sin phi is equals to sigma 1 minus sigma 3 by sigma 1 plus sigma 3, and phi is equals to sine inverse of major minus minor by major plus minor. This equation is very important in solving the questions. So this is very important, Nana. You please have to remember this one. This is very important for the logics. I'll tell you both the logics and basics I'm going to discuss. So both will be there. But this is the logic. The logic is, I can directly say from the Mohr circle. You see how I have explained this one. You please observe. This is the same phi r naught. In the case of the cohesionless soil, I can keep C 0. Just simple. If I keep C is equals to 0, if I keep C is equals to 0, then whatever the remaining value, if I keep C 0, then the remaining value is going to be sigma 1 minus sigma 3 by sigma 1 plus sigma 3. So in the case of the cohesionless soils, either you can go through this equation, and what is this alpha f? Again, you need to find out the alpha f. And what is this alpha f? 45 plus 5 by 2 is equals to tan inverse of root of sigma 1 by sigma 3. Is this easy? And this one is going to be easy. It's up to you. I'm leaving this. This is the basic from the plastic equilibrium equation, and this is the logic from the Mohr circle. Mind it, this equation, how I have measured, how I got this equation from this only now. So now, instead of remembering the equation directly, I am going to progressing towards the basic, and from this, if the soil is going to be cohesionless soil, and if the soil is going to be a cohesionless soil, then how to determine the C and phi value. C is equals to 0 and phi greater than 0. And see, some of the people are asking now, what is major and what is minor? Sir, major principal stress, minor principal stress. Sigma 1 is major principal stress and sigma 3 is going to be minor principal stress. Similarly, in the case of cohesive soils, look, in the case of the cohesive soils, so cohesive soils means pure or plastic clays, which means C greater than 0, phi is equals to 0 degrees. So, simply I can write as phi is equals to 0 degrees. If phi is equals to 0 degrees, if phi is equals to 0 degrees, then what happens? Please look again. In the case of the phi is equals to 0, you know that the failure envelope is going to be exactly horizontal. So now here phi is equals to 0 degrees and whatever this is nothing but a C. Look, now from plastic equilibrium equation, sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f. So here when phi is equals to 0 degrees, alpha f is equals to 45 degrees. Yes. And what is tan alpha f? 1. Tan 45, 1. Then sigma 1 is equals to sigma 3 plus 2c. See, 45 degrees means tan 45, 1, right? Don't ask me why the tan 45 is going to be 1, please. So sigma 1 is equals to sigma 3 plus 2c. Then from this, c is equals to sigma 1 minus sigma 3 by 2. The logic is from Mohr circle, if you draw the Mohr circle, if you draw the Mohr circle, this is sigma 3 and this is going to be sigma 1. Are Baba, by seeing the Mohr circle, can't you say the answer now? See, this is C, right? And if this is C, then what about this value? You please tell me. What about this value? See, in the case of the cohesive soils, phi 0, and whatever this intercept is nothing but C, right? And this C is nothing but tau f is equals to tau maximum. Yes or no? So logic is C is equals to tau maximum. You please tell me, what is this tau maximum? Sigma 1 minus sigma 3 by 2. How I got this value? Logically, see, the logic means here there is nothing. It's just a usage of the Mohr circle. That's it. So I hope you understood. See, I want this C. What is this C? The C is going to be vertical ordinate. What is the maximum vertical ordinate over here? Tau max. The maximum vertical ordinate is going to be tau max. So now what is meant by tau max over here? C is equals to tau max is equals to sigma 1 minus sigma 3 by 2. So this is for the cohesive soils, and now C5 soils. In the case of C5 soils, C greater than 0 and phi greater than 0 degrees. Both are there. In the case of the C5 soils, so far whatever the discussion we made in earlier things, yes. There is going to be sigma and here it is going to be tau. You know this is nothing but C and here it is going to be phi. So you have to use sigma 1 is equals to sigma 3 tan square alpha f plus 2c tan alpha f equations of it. See, I hope you understood the logics behind this, sir. Why you are discussing all these things, sir? Why I am discussing is, in the case of the examinations, my dear students, in the case of examinations, if I give you pure sand, which means phi is equals to 0. When phi is equals to 0, then what is our C value? When phi is equals to 0, the C value is going to be major principal stress minus minor principal stress by 2. Major principal stress minus minor principal stress by 2. And if I say phi is equals to 0, if C is equals to 0, then phi is equals to sine inverse of major principal stress minus minor principal stress by major principal stress plus minor principal stress. And in the case of cohesive soils, when phi is equals to 0, this is the logic. See, these points I want you to remember because I am going to use it for the questions. See, whatever the analysis I have made so far, this analysis is just simply for the sake of knowing when the failure plane occurs. What is the angle made by the failure plane? See, I took the same element everywhere. Please observe. I took the same element everywhere. If you observe, this is the element, same element. And here also I took the same element. You see, the element is going to be same. I'm on. From the starting onwards, I'm discussing about element. What are the stresses acting on element? Major and minor principal stress. And what is this plane? Failure plane. Now, today, whatever the discussion I made is, now listen, if this is a failure plane, what is the angle made by the failure plane? First of all, what is the angle made by the failure plane? Yes, alpha is equals to 45 plus 5 by 2. And based upon the phi value, I can conclude the failure shear stress can be less than or equals to a maximum. And then, what is the relation between the major principal stress, minor principal stress, and the soil properties? From this, we got the whatever this condition is going to be the plastic equilibrium condition. From this, I can say for pure sand, when C is equals to 0, phi value, and when phi is equals to 0, C value. Sir, example for the C5 soil, sir. C5 soil is going to be the example as silty clay or sandy clay or silty sand. So all these things comes under as a C5 soils only. That's not C5 means cohesion is there and friction is there. C5 means cohesion is there and friction is there. Okay. So just if you have understood these things, the later things are going to be very easy for you. You please observe over here once. Everybody have a look over here, please. So this is a previous gate question. For a sample of dry cohesionless soil with a friction angle phi, the failure plane will be inclined to the major principal plane by an angle. So what is the meaning of dry cohesionless soil? Whatever it is, so the failure plane will be inclined. The failure plane, this is a failure plane, will be inclined with respect to major principal plane. This is nothing but alpha f r naught. So what is alpha f? 45 plus 5 by 2. The answer is going to be 45 plus 5 by 2. Answer is D. So they have given some friction angle phi, and see why they have given phi is if it is a cohesive soil, then phi is equals to 0, right? In the same question, instead of cohesionless soil, if I mention you cohesive soil, then phi 0. When phi is equals to 0, then alpha f is equals to 45 degrees. There is an option for 45 degrees also. Keep that in your mind. Now, Yes, all these things requires the test details and all those things. So we'll see those things later. Now, as of now, you please go through these things and I'm going to utilize all these things later. So meanwhile, let me give you one question so that after this one, I'll give you a question. I have a question for you. So I'm giving you this question, example question. A soil sample is subjected to major principal stress of 2 kg per centimeter square and minor principal stress of 1.1 kg per centimeter square. So determine the normal and shear stress acting on a plane of yet 30 degrees to minor principal plane. Minor principal plane. See, this is the question I have given you. Please look over this. There are not many pole points now. You see, this is the question I am mentioning you. Now the solution is, you see, I have given you, this is a soil sample. Now observe. So I mentioned you, this is a soil sample which is subjected to major principal stress how much? 2 kg per centimeter square. Minor principal stress how much? How much? 1.1 kg per centimeter square. So this is a soil sample which is subjected to 2 kg per centimeter square as major and 1.1 kg per centimeter square as a minor. So now what I am asking you is, first of all, if this is a plane, that there is a plane. Now there is a plane and this plane will make, see, I am asking you what is the normal stress and what is the shear stress acting on the plane at 30 degrees to major principal plane or minor principal plane. So you know this is nothing but minor principal plane. Yes, but you know that whatever the alpha we take, alpha will be always angle with respect to major principal plane. So now whatever the angle they have given is this angle. So now what is alpha? This is 90 degrees. I hope you understood. See, I just made a small twist over here. That twist is minor principal plane. See, in this only I am going to discuss everything. Please wait for some moment, then you can get it at. So now the alpha is going to be how much here? Alpha is equals to 90 minus 30, which is going to be 60 degrees. So how to determine the sigma, sir? So you know sigma is nothing but sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos 2 alpha. So now you have a sigma 1. What is sigma 1? 2 plus 1.1 by 2 plus 2 minus 1.1 by 2 cos 2 into 60 degrees. So find out the sigma value, and similarly tau is nothing but sigma 1 minus sigma 3 by 2 sine 2 alpha. Sine 2 alpha. So now, yes, what is this value please? 2 minus 1.1 by 2 sine 2 into 60 degrees. So find out the tau value. The five values are going to be like 2 plus 1.1 by 2 plus 1.2 minus 1.1 by 2 into cos 120 plus 3.1 by 2. So this value is going to be 1.325 kg per centimeter square. And this value is going to be 2 minus 1.1 by 2 into sine 120, which is going to be 0.39 kg per centimeter square. You see this sigma, this is less than sigma 1 and more than sigma 3. So now, if the soil sample is going to be sand, see, I'm going to introduce one more topics over here. Now, I hope you understood how to determine the sigma and tau. So in the same question, B, if soil is pure sand, if soil is going to be pure sand, then angle made by failure plane would be, if it is going to be a pure sand. So now I discussed that this is a soil sample, and if it is going to be a pure sand, you know that the solution is, in the case of pure sand, phi is equals to 0 degrees. C is equals to 0 kilopascals. So just now I mentioned you, if you want to find out the alpha F, you know that alpha F is equals to 45 plus pi by 2. So I can tell you the both procedures from plastic equilibrium condition, sigma 1 is equals to sigma 3 tan square alpha F plus 2c tan alpha F. See, I want you to find out angle made by the failure plane. Understood or not? So for that you need to find out the phi value first, or you can find out here. So directly, now when C is equals to 0, this is going to be 0. Then sigma 1 is equals to sigma 3 tan square alpha F. Sigma 1 is equals to sigma 3 tan square alpha F. So now, if you observe, what is sigma 1 I have given? 2. So 2 is equals to 1.1 into tan square alpha F. So can you please find out the alpha F over here? Just simply 2 by 1.1, which is going to be root of answer and the tan inverse of the answer. So the alpha F is going to be 53.44 degrees. So what is alpha F? I got 53.44 degrees. Or the logic is when C is equals to 0, phi is equals to sine inverse of major minus minor, means major principal stress minus minor principal stress by major principal stress plus minor principal stress. See, I'm applying everything over here. At first, this is an element. What is the normal stress and shear stress acting? Okay. Now I am asking you, if the soil is going to be a pure sand, then what is the angle made by the failure plane would be? So what is the angle made by the failure plane would be? Now you see. So whatever the explanations I have made over here, if it is a corrosionless soil or pure sand, you know that when C is equals to 0, then phi is equals to sine inverse of major minus minor by major plus minor, principal stresses. Now phi is equals to sine inverse of major 2 minus 1.1 by 2 plus 1.1. So what is the phi value, please? Phi value is equals to 2 minus 1.1 by 2 plus 1.1, which is going to be 3.1. So sine inverse of answer, which is going to be 16.87 degrees. But I am asking you alpha f. So 45 plus 16.87 degrees by 2. So which is going to be again 53.44 degrees. 53.44 degrees. See, the meaning of this one is now. I hope, listen everybody. At first, you please look over. What is the angle I have given? 60 degrees, right? Yes or no? For 60 degrees of alpha, these are the normal stress and these are the shear stress. Now, what is the failure shear stressor over here? See, if I apply, if the soil is going to be a pure sand, then the soil element will fail at an alpha F of 53 degrees, 53.44 degrees. So I hope you understood. I hope you understood over here. So, what would be the phi value? Yeah. Yes. So now see, if soil is pure clay, then cohesion is dash. If soil is going to be pure clay, then phi is equals to 0, then C is equals to sigma 1 minus sigma 3 by 2. So 2 minus 1.1 by 2, which is going to be, I think so, 2 minus 1.1 by 2, which is going to be 0.45 kilonewton per meter square. See, the units of the question is going to be 0.45 kilonewton per meter square. I have given you this question and I made some modifications. So how to determine these values? That's all, everything I have been applied. So I hope you understood this question. And in this question, I used the earlier equations. This is the earlier equation and this is the earlier equation. And I changed the soil mass. If the soil is going to be pure sand, angle made by the failure plane would be how much? So if the soil is going to be pure clay, then what is the C value? Because in the case of pure clay, phi is equals to 0 degrees. So I hope you understood these things. Now, let's have a break. So, yes, kg per centimeter square. This is I'm sorry. This is a kg per centimeter square. Whatever the units I have given is in terms of kg per centimeter square. Sir, all fine grained soils are cohesive? No, need not be, because it depends upon the percentage of clay. Kg per centimeter square only. Yes, correct. Yes, so now it's 11:20. Have a break up to 11:35. Have a break of 15 minutes. See, these topics are See, I am taking time. That's the reason why you are not able to get the whole point. If it was a whole full day class, then you can understand from the starting point to ending point. See, in the shear strength chapter, every point is going to be connectivity. So that is the reason why I am asking you today. See, tomorrow there won't be any class. What you need to do is today I'll be taking a little bit more time so that I can complete some portion of the syllabus. So you please go through every point in the notes. You please go through every point in the notes. Then you can understand much more better. Let's have a break and come by 11:40, 20 minutes. 11:40, please have a break. Yes, yes, yes. So I hope people are there here. So now you see the solution for this. See the solution for this. See, earlier I have given you application of the soil mass over here. So now what I want to say here is, so I want to find out the shear strength. Yes. So you know the equation of the shear strength, right? So now I need to find out the shear strength. S is equals to C plus sigma into tan phi. Yes. And if you observe whatever the variables I have given over here, this is nothing but the drained parameters. Yes or no? C dash phi dash means drained parameters, which means effective stress analysis. Yes or no? Effective stress analysis. So S is equals to C dash plus sigma dash into tan phi dash. And moreover, I have given C dash is equals to 0. Or else I can say directly, as a soil is a sandy soil mass. Though directly I can say the soil is going to be sandy soil mass. So as the soil is a sandy soil, definitely I told you in the starting point. So you please look over this point. For granular soils, generally tests are conducted under drained conditions. Yes or no? So that's the reason why I gave you directly over here. Now we need to find out the effective stress. So if you find out the effective stress at 5 meters, then you can find out any other thing. So let's find out the effective stress. For finding the effective stress, you know the gamma D, and given for sand, gamma D is equals to G gamma W by 1 plus C. So what is E? G gamma W, C. First of all, effective stress at 5 meters is nothing but gamma D into 2 plus gamma dash into 3. I hope you remember these conditions, right? Below the water table soil is gamma becomes gamma dash. So now gamma D into 2 plus gamma dash into 3. So first we need to find out the gamma dash. I have given you the gamma D, but do you know the gamma sat or gamma dash? No. For that, you know gamma D is equals to G gamma W by 1 plus C. From this, E is equals to G gamma W by gamma D minus 1. So 2.7 into kilonewton, right? 9.81 by gamma D 17 minus 1. So what is the E value we got? E value is equals to 2.7 into 9.81 by 17 minus by 17 minus 1. So which is going to be 0.56. That's the void ratio. Yes. Now from this we can find out the gamma sat is equals to G plus E by 1 plus E into gamma W. So 2.7 plus 0.56 by 1 plus 0.56 into 9.81. So plus 2.7 by 1.56 into 9.81, which is going to be 20.49 kilonewton per meter cube. So now effective stress at 5 meters is equals to gamma D into 2 plus gamma dash means gamma sat minus gamma W into 3. 17 into 2 plus gamma sat. How much gamma sat, please? 20.49 minus 9.81 into 3. So please tell me this value, effective stress at 5 meters. What is the value over here? 17 into 2 plus 20.49 minus 9.81 into 3 plus 34. So this value 66.04 kilopascals. Now what is the shear strength? As a C dash is equals to 0, sigma dash into tan phi dash. 66.04 into tan 30 degrees. So which means 38.13 kilopascals. This is the shear strength. See, what is the only thing that I have added extra here is a shear strength. That's it. You know the equation, right? And you know how to determine the effective stress. So if you know how to determine the effective stress, then you can find out the value directly. So now, yes. So once you find out these values, now if water table, if water table rises to ground level, change in shear strength. You tell me, if water table rises to ground level, if water table rises to ground level, then effective stress is going to be gamma dash into 5, which means 20.49 minus 9.81 into 5. So can you please tell me this value? 20.49 minus 9.81 into 5, which is going to be 53.4 kilopascals, which is going to be 53.4 kilopascals. Then what is the shear strength over here? 53.4 into tan 30, which means tan 30 into 53.4. So the value is going to be 30.83 kilopascals. Then the change in shear strength. I'm just asking you the change. I'm not asking you anything. So 30.83 minus 38.13, which is going to be minus 7.299. So we can take it as a 7.30, which means shear strength reduced by 7.3 kilopascals. Shear strength reduced by 7.3 kilopascals. See, look, whatever the question I have given, this is the question. So this was one question. See, these are the extra questions I'm making. So I'll be taking more questions in this chapter so that I can cover all the topics. Don't worry about that. Now, I hope you understood. Yes, we can directly find out the stress change. See here, the change means what is the initial? This one. What is the final? This one. Final minus initial. So initial is that. See, the magnitude is going to be 7.3. The magnitude is 7.3. The value is going to be 7.3 only. But I want to show you here that the shear strength is reduced or increased. Reduced. See, we know that if water table rises, effective stress decreases. When effective stress decreases, shear strength is also going to be decreases. So I hope you understood. Now let's come to the experimental procedures. So I have given you a lot of analysis over here. This analysis will be useful everywhere. So now coming to the experimental procedures. what are the experimental procedures we are going to conduct? Number one, direct shear test or box shear test. Direct shear test or box shear test. Number two, triaxial test, triaxial shear test. Number three, triaxial shear test. Number three, unconfined compression test. And number four, vane shear test. So these are the type of tests that we are going to discuss. And this box shear test is mainly suitable for granular soils, which means soils that are having high drainage. And this is for all types of soils. And unconfined compression test, this is for saturated clays. And this is also for saturated clays. And mind it, this can be field or lab test. It can be a field test or it can be a lab test also. So these are the tests that we are going to discuss. And now the first one is going to be direct shear test. Number one, direct or box shear test. Direct or box shear test. See, in the case of the direct or box shear test, I told you for every test there are four things that you need to look: aim, apparatus, procedure, and results. So first of all, the aim over here is aim to determine C and phi. As I told you, the C and phi are not going to be constant. They depends upon the rate of loading. They depends upon the type of drainage. They depends upon the type of soil. They depends upon the type of test. So for different soils under different conditions, how to determine this C and phi? So now in the case of the direct or box shear test, if you observe, first of all, we need to look over the apparatus. So in the case of the direct, in the case of the direct or box shear test, okay. So now in the case of the direct or box shear test, so the first thing is, what is our aim? To determine the C comma phi. And what is the type of soil? I told you mainly suitable for granular soils. Why? I'll tell you later, means during the procedure. Now coming to the apparatus. So in the case of this direct box shear test, So now, in the case of the direct box shear test, there are two boxes. Now, please listen, look. See, in the case of the direct box shear test, you are going to have a direct box, means a shear box. I hope you have conducted this test in your laboratory. That shear box is a hollow inside, and in the plan it is going to be a square. In the plan, if you see the top view, it is going to be a square. Likewise, the two boxes are going to be there. So now, what we are going to do is, yes. So these are the boxes that I'm going to have. Now, if you observe, this is a box, and this box is made up of steel. Now, at the top and bottom, we are going to place a porous stones. You know the meaning of the porous stones or porous plates, right? Whatever, this is nothing but a porous plate, and this is also going to be a porous plate. Now, these are nothing but the shear boxes. In the top view, if you observe, in the top view, it looks like this. In top view, means in plan, this is a shear box, and this is nothing but the porous plate, and porous plates are there. So then we are going to rest everything on a rigid platform. There is going to be a rigid platform. So, and to this rigid platform on the sides, to the rigid platform on the sides, we are going to connect to this. Pivot. And there is one more dial gauge over here. So on the top of it, we are going to apply. There is a loading plate. So now you please look over here. This is a loading plate. So what we are going to do in the case of the box shear test is, what we are going to do in the case of the box shear test is, look, in the case of the box shear test, first of all, you are going to take two boxes. One is a top box and is going to be the bottom box. Two portions are there. So then we are going to fill this inside with the soil mass, whom C5 values we need to find out. First of all, what we are going to do is we are going to apply a vertical load of P. A vertical load of P is going to be applied on the top. A vertical load of P is going to be applied on the top. And then you see there is a small interface present over here or not? There is a small interface present over here. Then what you are going to do is soil is going to be sheared. See, this is nothing but a soil mass, 1 cup, other cup, 1 cup, other cup. You see 1 cup, other cup. Now what you do is you apply a horizontal force. In the case of the laboratory, there is a horizontal force. You apply a horizontal force. When you apply a horizontal force, these cups are going to be slide or not? Yes or no? So now soil is going to be sheared by applying a horizontal force. So first you apply a vertical load, and you know that due to vertical load, soil undergoes compression. Point number 1. First you apply a vertical load. This is a vertical load, and this is a shear load or shear force, or I can say okay, fine, shear force. So then what you are going to do is now first you apply the vertical load. Next you are going to make sure the soil is going to be sheared. After application of vertical load, soil gets sheared by applying a horizontal force, at constant strain rate. See, mind it, after application of the vertical load, now you apply a horizontal load. Now this is going to be applied, that load, at a constant strain rate. Mind it, I'm telling you one more point over here. We always do strain controlled tests. We always do strain controlled test. What is the meaning of a strain controlled test, sir? Strain means deformation per unit length. Yes or no? See, always we make sure the strain is going to be uniform, which means if the soil mass is going to be shears by 1 centimeter, next 2, next 3, 4, 5. So we are going to apply the strain control. There are 2 types of tests: stress controlled, strain controlled. Here I am applying the horizontal force at a constant strain rate, and note down the shear force at which soil gets sheared and fail. So after application of the vertical load, soil gets sheared by applying a horizontal force at a constant strain rate. Note down the shear force at which soil gets sheared and fail. So now you see this is a dial gauge. The dial gauge is used for what? For finding the compression and for finding the shear. See, when you apply vertical load, soil will undergo compression, and when you apply shear, soil will undergo displacement. That displacement is going to be measured by using the dial gauge. But the point what we required over here is, now let's take out that element. Let's take out that element. Whatever the soil element, this is the soil element. So now from the soil element, you know that this is the horizontal plane, because you see these planes, whatever this plane is going to be a horizontal plane where we can keep one box above and other box below. So now if you observe, now due to the normal load, then there must be normal stress. So what is the normal stress, sir? The normal stress is nothing but normal load by area of box, which means P by box area. Sir, what is the box area, sir? You please observe over here. So this is a planar nut. This shear box has some area, plan area, or we can get it as a nominal area. Similarly, in the horizontal direction, whatever the shear stress you are going to apply, this is a shear stress, and that shear stress is going to be find out as a shear force by area of box. Sir, why you are using same area for here, sir? Sir, you know that when you apply the load, this area is going to be the cross-section area for the vertical load. This area is going to be the cross-section area for the vertical load. And the same area will be the surface area for the horizontal load. So don't ask me why you used both areas are same. So now what I do is, once you know this, see, first noting down the normal stress and then the shear stress. So then slowly note down the shear force at which a soil gets sheared and fail. So now slowly what happens is, so if you observe this, for the corresponding normal force, and there is going to be the shear force at a failure, and this failure is going to be, this is known as a failure plane. So this is what mentioned in the case of the direct shear test. So first of all, in direct shear test, what we are going to do is, we keep the boxes, we apply the load, and then we shear it in the horizontal direction. Note down the shear force at which soil is going to be sheared and gets failed. So whatever the failure we got is nothing but tau F. Now conduct conduct similarly test on 2 to 3 identical specimens and note down conduct a similar test on the 2 to 3 identical specimens at different vertical loads and note down the shear stress yet failure. You observe over here, the number one is, we are not going to find out the stresses directly. What I do is, I apply the vertical load and I apply the horizontal load at a constant strain rate and note down at what load. See, these are the two planes, right? Observe everybody. These are two planes. When I apply a horizontal load, one of the plane is going to be starts to shear. Whenever it is going to be out of control, note down the shear force at which it is going to be move off. And then whatever the plane here is going to be failure plane. So here, if you observe, this is a failure plane. By conducting this test on identical specimens, 2 to 3 identical specimens. Now note down the shear stress at failure. So yes, now whatever the normal stress and whatever the shear stress at failure. Whatever the normal stress and whatever the shear stress at failure. See, at first, let's say I applied 50 kilopascals in terms of kilopascals. Okay. At first, I applied 50 kilopascals. For a vertical stress of 50 kilopascals, soil will undergo compression. Now think carefully. Baba, if this is soil, you apply vertical load, soil will undergo compression. When the soil undergoes compression, the interlocking between particles would be more. Yes. Then the interlocking is going to be more. Then what happens over here is, and after that, then when you are going to shear, then the soil will offer some resistance, and you need to find out that resistance as a shear stress at a failure. And then you are going to apply, let's say the shear stress at failure we have measured as 35. Now my question for you, if I apply 100 kilopascals of the normal stress, if I apply 100 kilopascals of the normal stress, now you tell me, Baba, if you apply more vertical load, more compression, and more resistance to shearing. More resistance to shearing means, let's say this value is going to be around, let me take it as some 60 or 70. Just for the sake of explanation only I'm taking, is going to be 70 and so on. So first of all, you need to find out the normal stress and shear stress at failure, as whatever the shear force where the failure is going to be happen by area of box. So the normal load by area, shear force by area, you find out these values. Now you plot a you plot these points, please. Once I plot the points, now for 50 normal stress, and this is going to be the shear stress. Yes. And for 100 normal stress, this is normal stress, and this is going to be the shear stress. For 100 normal stress, this is going to be the shear stress. For 150 normal stress, this is going to be the shear stress. And now, if I join all those points, by taking a best suitable line, now this is nothing but failure envelope. This is nothing but failure envelope. Why? Because failure envelope means locus of failure stresses. Locus of failure stresses. See, what I done is, for a particular normal load, what is the shear force at failure? So what I have done is, on the same soil mass at a different normal stresses, at a various normal stresses, I'm finding what is the shear stress or what is the resistance offered by the soil mass. Now, by plotting all those points, you see, by plotting all those points, and if I draw a best suitable line, then I can get the failure envelope, because you know failure envelope is nothing but the locus of the failure stresses, and whatever the angle made by the failure envelope is phi, and this is going to be C, where C is known as a cohesion intercept. C is known as cohesion intercept. Generally, in the case of the direct shear test, the C value is going to be very less. This is the test procedure. Sir, how to calculate the magnitude of shear force? See, that shear force will be calculated this pivot reading. That pivot ring would be there. This pivot ring reads shear force. So pivot dial gauge reading would be there. That will be reading the shear force. And now More than normal load, less the shear stress. No, more than normal load, more the shear stress. You know why, sir? Why you take the same area for both? I know you people ask the same question. I am applying the force in this direction. Then the top body will move. Okay, fine. You thinking in that way. Okay, okay, fine. I got it. I got your point. Okay. Everybody, you please observe this is H, and you please observe this is bottom is fixed and top is free to move. Bottom is fixed and top is free to move. When this is going to be moved, it will apply some force on this gauge. Now this pivot ring will read the shear force. So now this is about the determination of the C and phi. This is about the determination of C and phi. So simply what I did is I apply the test, find out the shear stress, and then you find out the means you draw the plane, then you can find out the values of C and phi. Sir, analytically in examination what to do, sir? Analytically in examination means in exam, this is lab, right? Analytically now what to do, sir? How to find out the shear strength, sir? Sir, S is nothing but C plus sigma into tan phi. I hope you know that. And you know tau f at a failure is nothing but shear strength or not. So from data, what I can write is I have two equations. So you know that tau f is nothing but S is equals to C plus sigma and phi. From data, the tau f is nothing but 35 is equals to C plus 50 into tan phi. 50 into tan phi. And next 70 is equals to, see this data. From the data, 70 is equals to C plus 100 into tan phi. This is from data 1, this is from data 2. This is from data 1 and this is from data 2. So now what I do is, you know that 2 minus 1, if you do, then C will be gets cancelled down. And once the C is going to be gets cancelled down, then 70 minus 35, 35 is equals to 100 minus 50, 50 tan phi, 50 tan phi. Then what is phi value? Tan inverse of 3.5 by 5. What is this phi value, please? Which is going to be 34.99 degrees or approximately 35 degrees. Sir, what about the phi values? What about the C values are here? The C value is going to be like, you observe, please, you observe by solving the C value. Phi value is going to be 35 and C value, see, you observe, can I keep the 50 tan phi? See, what is the 50 tan phi here? 35, right? If I keep 50 tan phi as 35, if I keep 50 tan phi as 35, then 50 tan phi, 35, 35 is equals to C plus 35, then C value is going to be 0 kilopascals. So for this data, if I draw the failure envelope, then the failure envelope is going to be passing like phi is equals to 35 degrees and C is equals to 0. So for this data, analytically, I'm going to provide over here. See, first I observed the procedure and I said you the procedure. So in the procedure, I have explained you how to determine the normal stress and how to determine the shear stress. So whatever the area, cross-section area for normal stress will be the surface area for the shear stress. So those are the basic things that you need to know. So that's about the test procedure, but that's not the end. That's not the end. So what is the point over here is, look, the advantages of this test is, first of all, now, see, Advantages. Test is simple and less time taking. Test is simple and less time taking. This is one of the best advantage, but there are a lot of disadvantages. See, these advantages and disadvantages are very, very important in the case of the ESC because they can frame a question based upon this also. Now, you see here, whatever the failure plane is there or not. What is this failure plane? Failure plane is a horizontal or not? Yes. See, in the case of the direct shear test, do you think, I'm asking you a question, do you think the failure plane needs to be horizontal every time? No. The failure plane need not be horizontal. So here, the disadvantage, first disadvantage is a failure plane was predetermined as a horizontal. Failure plane was predetermined as horizontal. So that is the biggest disadvantage, which is not true for every case. Which is not true for every soil. See, failure occurs on the weakest plane. Failure occurs on the weakest plane. But here what they mentioned is the failure is going to happen on which plane? Horizontal plane. And second one is, you observe, if I provide a porous stone, then if I take a saturated soil, you please tell me now, if I take a saturated soil mass, in the case of the saturated soil mass, when you apply the vertical load, what happens? Think and say, see, I'm applying some vertical load or not. If it is a saturated soil, when an external load is applied on a fully saturated soil, excess pore pressure will develop. And now, as it is a porous plate, the water will dissipate through the porous plate or not? When the water is going to dissipate, is it a drained condition or undrained condition? Think and say. See, I am providing you a porous plate, right? If I go for the saturated soil mass, then due to this porous plate, the drainage is going to be passed. You cannot control the drainage. Can you control the drainage over here? Can you tell me how much excess pressure will be developed? No. See, as there is a porous plate, no control of drainage. This test is conducted only under drained conditions, not under undrained condition. This test is conducted only under drained condition, not under undrained condition. No control over drainage and no pore water pressure measurement. No pore water pressure measurement. So now there is no control over the drainage and there is no pore water pressure measurement. So this test suitable under drained conditions only. Drained conditions only. Yeah. So no control over the drainage. So no pore water pressure measurement. Test is suitable under drainage conditions only. And moreover that, you see, whatever the area I took, you observe what is the contact area over here. This is the contact area. Yes or no? But while I was measuring, which area I am taking? While I was measuring, which area I am taking? I am taking area of the box. So this is the actual area, but I am taking the area of the box. So the next one is nominal area applied is not correct for finding normal and shear stress at failure. So whatever the nominal area means, so whatever the area of box I have applied is not true, because this is the area I have to consider, right? So in this portion only there is a contact. Once there is a shearing, you please see, is there any contact over here? No. Is there any contact over here? No. So these are the disadvantages. See, I am taking more time for the sake of ESC people. I got to know that from some of the ESC people has given feedback in such a way. We have not satisfied with the ESC point of view. So that's the reason why I'm giving more point for the ESC also. These points are important for the ESC. For gate, the procedure is going to be important. I have discussed this procedure already. Now, which means now the note point is going to be direct shear test is suitable for freely drained soils. Example, granular soils. And as failure plane predetermined, this test is suitable for soils with fissures or cracks. So what is the meaning of this one, sir? I hope you might have seen a drought zone areas, drought areas would be there or not. So in your area, so if there is a drought condition, if you look over those barren lands, how does the top surface of the land looks like? There must be a lot of cracks would be there or not? There must be a lot of cracks. And if you take such type of soils which have a lot of cracks, already in this one, the failure plane is going to be predetermined. So no matter how many cracks in that, the failure will happen only in the horizontal plane only. So these are some of the advantages, disadvantages that we are going to see, and some of the note points that you need to require for the gate examination. The whole process I do take as apply the vertical load, note down the normal stress, apply the horizontal force, note down at which it is going to be failed by means of the pivot ring, and plot it on a table, draw the graph, whatever the locus of these failure points represents the failure envelope, and these are going to be C and 5. Generally the C value is going to be very, very less. Generally the C value is going to be very less. So C value is going to be very less. Now let's see the results from the triaxial test. Apart from this, we are going to give some more results from the triaxial test. Results from direct shear test, not a triaxial test. I'm going fast. More. Yeah, I'll take an example. I'll take an example. Once we complete this, then I'll take an example with this. So actually in the feedback, I got a lot of points like going too slow and need to be fast. Explain failure plane with example. See, Nana, this failure plane is already predetermined. Not you or not me. So example, I can take fissured clay. Fissured clay means if I take a soil mass, this is a clay, means a dry clay. And if you observe, there are a lot of cracks over here. These are nothing but fissures. And if this is a dry clay, see, for the dry clay, you can use it for the dry clay, you can go for the direct shear test because there is no water, right? When there is no water, there is no problem. For the same experiment, yes, the next one, see, in order to go in order to remove all these disadvantages, we need to go for the triaxial shear test. And that we'll see later. But as of now, let's come to the results from the direct shear test. Whatever I am going to say, this point is very, 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 very important. Please listen to these points clearly. Hey Baba, there is no pore water pressure measurement device. Pore water pressure measurement device. So you cannot find out the excess pore water pressure. You need to allow the water completely so that excess pressure should zero. That's disadvantage only. Fine. So now let's see whatever the points I'm going to represent. These points are very, very important. Please have a look. Now let's take a loose sand. Let's take a loose sand. Now this is going to be one loose sand. See, in the case of the loose sand, now if I apply shearing along this plane, if I apply shearing, you please look, if I apply along this plane shearing, now these particles will slide in this direction. These particles will slide. See, I'm showing you the direction. See, these are the particles. Yes. So when I apply the shearing, then these particles will slide. Then the particles will slide. When the particles will slide, what happens over here is, when the particles are going to be slide, then you see this particle will come into this place or not. This particle will come into this position, and this particle will come into this position, and this particle will come into this position. Now, have a look clearly. In the case of the loose sand, when I apply a shearing, what happens is, now keep the bottom particles as the same. Now keep the bottom particles are same, but as these particles move, now the first particle will move to this position by orientation. See, the particle will orient in this fashion. So similarly, the second particle will move over here, third particle will move over here, fourth particle will move over here. So if I apply the shearing, now if you observe, the particles are going to be moved towards this one. See, when you apply the shearing, the each and every solid particle will roll, which means a sliding will be happening as a roller, rolling, sliding. So now due to that, if you observe from this point to this point, can I say this is nothing but a cubical arrangement? You remember the chapter number 2, cubical arrangement. If I shear, then it is going to be behaves like a diagonal arrangement or not? Then this is going to be behaves like a dense sand. Then it is going to be behaves like a dense sand. So what I want to say here is, listen to me carefully. In the case of the loose sand, number one, if a loose sand gets sheared, if a loose sand gets sheared, then particles will slide over each other. Particles will slide over each other and configuration changes from one to two as shown in figure. Configuration is going to be changes from 1 to 2. I hope you understood the point over here. So when you apply the shearing, the particles will be slide over each other and the configuration changes from loose sand to dense sand. Are Baba, loose sand to dense sand means the soil mass will undergo compression or expansion, compression. So as shown in the figure, and hence compression occurs and soil becomes dense sand. See, I hope you understood this point. So the point that you need to look over here is, so compression is going to be occur and initially loose sand, particles will slide and behaves like a dense sand. This is a point number one. Now, what if I shear the soil mass in the case of dense sand? What if I shear the soil mass in the case of dense sand? So let's see the next one. See, these are the shear characteristics of the sand, Nana. These are the shear characteristics of the sand. Now, in the case of the in the case of the dense sand, in dense sand, 20 to 30% of shear strength is due to interlocking between particles. Interlocking between the particles. Now, everybody, sir, what is the meaning of interlock, sir? Sir, you see these knuckles, right? Observe, please, over here. These are 2 points I want to show you. Yes. So I hope you can see these knuckle points over here. So whatever this point, knuckles. So now, earlier the sand particles are going to be like this, loose sand, which means the loose sand has a more wide space. Now, when it gets a shear, see, this is the original position. Now, when it gets a shear, now you see how the arrangement is going to be looking like. Earlier, this is the arrangement. Now, when it gets a shear, this is the arrangement. Earlier and now shear. So now you see the locking between my hands is going to be more, right? Which means contact is going to be more. So in the case of the dense state, due to this contact, due to this interlocking, strength is going to be more. Sir, now you see, you observe over here. At first, this is the position. Please have a look. At first, this is the position. Now, when you apply the shearing, shearing means in this direction. When I applying the shearing, you see the loose state will becomes denser state by interlocking. Now, if I sheared continuously, what happens to here? If I sheared continuously, first the volume will undergoes more compression and slowly this interlocking breaks down. After some loading, the interlocking breaks down, and again after shearing, now this is going to be behaves like a loosest state. Now this is going to behave like a loosest state. So at first, this is a loose. At first, this is the loose, and due to shearing, interlocking increases, and then soil becomes dense. If you apply more load, then the interlocking will break down and soil will behave like again as a loose. So this interconnection is going to be changes. This interconnection will be changes from here to here and again here to here. So now if a dense sand gets sheared, initially it undergoes compression, and later interlocking between particles breaks. See, initially it undergoes compression due to interlocking, and later interlocking between particles breaks and soil starts to behave like a loose sand. See, if the dense sand is going to be behaves like a loose sand, you see, observe this portion now, this is going to be behaves like this one, and dilation occurs. Dilation means increase in volume. Dilation occurs, results in negative pore water pressure. Results in negative pore water pressure. So now, due to the dilation, what happens is the void space is going to be more. I told you clearly earlier, Baba, if this is a void space, or if this is a void space, if the void space under compression, whatever the water in the void space will have more pressure. If the void space is going to be dilated, then the water will be less and the pressure exerted by water will decrease, which undergoes to negative pore water pressure. So here hence compression occurs and soil becomes dense and results in positive pore water pressure. So if you can understand this figure now, then you can understand whatever the points I have written over here. Why today less number of people have been attended? Why today very less number of people are attended? I don't know. See, these points are very, very important because the graphs that I am going to give. So if it is Sunday, then getting bored, I think. So then what I have to do then? I am making more number of examples. I am making sure it is going to be understand too or not. Even if it's boring for you, then what can I do? Okay, fine. Fine. Your 0. Yeah. So now let's see. Okay. So this is the point I want to mention. So due to this, what happens over here? If a loose sand gets a shear, particles will slide over and configuration changes from 1 to 2, as shown in the figure. Similarly, breaks, soil starts to behave like a sand. So here configuration changes from a 1 2 to 1. Here configuration changes from 2 to 1. So now this is a point number 1 and this is a point number 2, which was happened. See why I have given you, observe over here, this is the horizontal plane or not. So now based upon this, the results are going to be like, first the results are like A, on x-axis shear strain, on x-axis shear strain, on y-axis change in volume plus, and this is going to be minus. On x-axis a shear strain, and y-axis a change in volume. Now you see, in the case of loose sand, what happens? Compression occurs or dilation occurs? Compression is going to be occurs. So due to this compression, what is the meaning of compression? Volume is going to be changes. So from the point number 1, from the point number 1, from the point number 1, if you observe, see, in the case of the loose sand, you see, I'm going to take these 2 points only. In the case of the loose sand, what happens? Compression is going to be occurs. Remember, compression means reduction in the volume or not? In the case of loose sand, volume will get decreases. So this is representation of loose sand. Why, sir? Sir, in the case of loose sand, sir, during the shearing, sir, volume, compression occurs, sir. Compression occurs. So I have written this point over here. Compression occurs. So due to that, compression volume is going to be decreases. So first one. And second one, if it is a dense sand, initially it undergoes compression. Initially it undergoes compression and later interlocking between the particles will break and soil starts to behave like a loose sand and dilation is going to be occur. So in the case of dense sand, yet first, the soil will undergo light compression and then there is a dilation. So what is the meaning of dilation, sir? Dilation means increase in the volume, sir. So now here what happens over here is at first compression and then the soil starts to dilate. So whatever this increase in the volume, this is due to dilation. And mind it, then this is going to be a dense sand or not? I hope you can understand this. I have explained that. First, you please look over the point number 2. If a dense sand gets a shear, initially it undergoes compression. Yes, initially it undergoes compression. What is the meaning of compression? Reduction in the volume. The meaning of compression is reduction in the volume. And then later, when the interlocking between the particles break down, then what happens over here is the soil starts to behave like a loose sand and dilation occurs. And the dilation is going to be happening. Similarly, dilatancy and dilation are different. Dilatancy is different and dilation is different. Dilation means increasing volume. Dilatancy is a process that is different. Now, same again. This is shear strain. And now this is a pore water pressure. Positive pore water pressure and negative pore water pressure. Positive pore water pressure and negative pore water pressure. So now you see in the case of the positive pore water pressure and negative pore water pressure. See, this delta U is nothing but pore water pressure, Nana. Don't think that this is pore excess pore pressure. So now if you see in the case of the loose sand, due to compression, positive pore water pressure is going to be developed. Yes. So first in the case of the loose sand, now if it is a loose sand, due to dilation, due to compression, the positive pore water pressure is going to be handled. So this is for the loose sand. And in the case of the dense sand, at first it undergoes compression. So the positive pore water pressure is positive. And then due to dilation, the positive pore water pressure becomes negative. This is going to be dense sand. Here is going to be dense sand. So at first, this is due to dilation. Every point I have represented earlier, you please go. Loose sand. So then results in positive pore water pressure. Dense sand, initially compression, positive, and then due to dilation, negative pore water pressure. And see, shear, strain, and stress. Shear, strain, and stress. See, in the case of the loose sand, as you increase the load, as you increase the strain. See, in the case of the loose sand, as you increase the strain, then the stress is going to be directly proportional. The stress is going to be directly proportional. So in the case of the loose sand, as the strain increases, the stress increases directly like this. There is no peak point. There is no peak point. So now this is loose sand. But in the case of the dense sand, what happens over here is, observe carefully. In the case of the dense sand, you please see, at first the compression is going to be more, and later interlocking between particles breaks or not. When the interlocking breaks, suddenly the stress is going to be decreases. So now you see, at first compared to the loose sand, the dense sand stress is going to be more and reaches the peak. Now due to breaking of the interlocking, now the stress starts to decrease and reaches the critical. And this is also going to be critical. So whatever the portion I want to represent over here, the basic difference between the loose sand and the dense sand, you see, this portion is there or not? This is for the dense sand. Sir, why in the case of the dense sand and loose sand this is different, sir? And this portion is, this is due to interlocking. So now what I want to say over here, let's go back again. In the case of the dense sand, 20 to 30% of the shear strength is due to whom? Interlocking between the particles. So compared to in loose sand interlocking is insignificant. You can write that point also. So in loose sand, interlocking is insignificant. Interlocking is going to be insignificant. So in the case of the dense sand, what happens is, In the case of the dense sand, what happens is due to the interlocking, the strength is going to be more. See, I'm just focusing over, though I am giving you a lot of information over here. If you really understand, focusing 2 points. When you shear, loose become dense. Compression occurs, pore water pressure becomes positive. And when you shear dense, at first it compresses and then it is going to be again behaves like a bilateral. So first the strength is increases and then due to breaking of interlocking, the strength decreases. So this is the peak and this is the critical. The last one, this I'm telling you, the people who are ESC, if you go to the previous ESC questions, based upon this n number of questions has been there. Based upon the just 1 point I mentioned, you can solve any question. Now, D, last one. Shear strain and void ratio on the x-axis, means y-axis, shear strain. So now you see, compared to dense state, loose state has a more void ratio. Yes or no? Yes. Compared to dense state, loose state has the more void ratio. And this is going to be the densest void ratio. So in the case of the loose state, in loose sand, soil will undergo compression. What is the meaning of compression? Compression means a reduction in the volume. You see, as the volume decreases, the void ratio also decreases and reaches to some point over here. Yes or no? So now this is for whom? Loose sand. In the case of the loose sand, due to compression, as the volume decreases, the void ratio also decreases. Now, coming to the dense sand. In the case of the dense sand, initially volume decrease means initially void ratio decrease, and then due to dilation, volume starts to increase. So in the dense sand, due to dilation, volume starts to increase. When the volume is going to be increases, then the void ratio is going to be increases, and almost at certain point, both are going to be same. This is a dense sand. And whatever the void ratio at which almost they are going to be same, this is known as a critical void ratio. Whatever this is known as critical line, and E0 is critical void ratio. Some of the previous ESC questions they said as, now if the void ratio of the sample is more than the critical void ratio, if the void ratio of the sample is more than the critical void, this is critical void ratio. If void ratio is more than the critical void ratio, then you are going to call it as the loose sand. If the void ratio of the soil is less than the critical void ratio, we call it as a dense sand. And in the case of the, if a soil has a peak strength, then you are going to call it as dense sand. And whatever the peak is due to whom? Interlocking. And how much strength is due to interlocking? 20 to 30% of the strength is due to interlocking. Okay. So, and then in the case of the negative pore water pressure occurs when there is a dilation. Compression, positive pore water pressure. Dilation, negative pore water pressure. Now I go to the starting points over here. I hope you have seen this one. You see, foundation on the clays, earth dams, earth fields. Here, this is going to be compression. Due to compression, when you construct, then definitely there is a compression or not. Then you are going to say it as a positive pore water pressure. And when there is a dilation, there is a negative pore water pressure. So that's all with this. And the one more note point I want to mention over here is this is a D. The note point over here is like in sands, behavior change is same in clays. Same in clays. Loose sand and normally consolidated clay are similar. Dense sand and OCC are similar. You see, like in sands, behavior change is same in clays also. So behavioral change is same in clays also. So whatever the loose sand I have explained over here, the same way now, if you go for the clay also, the same thing is going to be happen. In the case of the clay also, the same thing is going to be happen. But in sands, we call it as a friction. In clays, we call it as a cohesion. So the same thing, whatever the figures I represent over here, so in the case of the time of continue next class, it's confusing and boring. We have tried so much, we're tired so much. If you continue for some, our heads will automatically break. So yes, due to interlocking, the entire strength is going to be break. This is a strength due to interlocking, and whatever the strength due to interlocking has been breakdown or not. Yes. So what I want to conclude over here is like in sands, behavioral change is the same in the clays. Loose sand and NCC are similar to each other. Dense sand and OC are similar to each other. So with this, I completed the direct shear test. And if you give me a few minutes, then I'll be conclude these sessions also. Why I'm saving all these questions is tomorrow, I mean day after tomorrow, the very important thing in this chapter, triaxial shear test will be coming, and that's very important. Yes, have a look about this question once. This was a GATE 2000 means a 1998 question, and this type of questions has asked in IAS also. Please have a look once. First, the stress strain behavior of a soil is going to be due to. You please observe, just now I said you, just now I mentioned you. You see the curve 1 and curve 2. You know this curve 1 is known as a dense sand or over consolidated clays. Just now I said you dense sand and OCC behavior is same. Behavior is same. So now similarly, this is going to be loose sand or NCC. NCC means normally consolidated clay. See, when I take sand, it's loose. Then I can say in clay that is going to be NCC because loose sands are more compressible than the dense sand. NCC is more compressible than the OCC. So now the stress strain behavior as shown in the figure is corresponding to curve 1, dense sand and over consolidated clay, curve 2, loose sand and normally consolidated clay. So answer is going to be C. If you have any doubt, you please go through here. Then I have said all those points. Yes. So with this, I'll conclude for today. Today's topic I will be concluding, and we'll be solving the questions in the next session. So with this, I've done with the direct shear test. I hope you understood well. If not, you please go through the notes once again, because I know it's a little bit tricky topic, but I'm telling you, once you go through the notes, I have given every point, pinpoint over there clearly. You please go through each and every point, then you can understand much more better. Okay, so the people who wants to leave, they can leave. And now I'm going to take some portion of a doubt clearing session. So now the people who wants to do, they can leave. They can leave. Now let's see some of the doubt clearing session. Sir, anyhow, we are applying horizontal shear force at constant strain rate. We find the change in contact area with respect to strain rate. No, Mr. Kaushik, you can't find that. It is difficult to find out. Sir, how nominal area is not correct? This condition. Yes. See, the nominal area means area of the box. But what is the actual area? This is the actual area. So the nominal area is not going to be correct. Negative pore water pressure means capillary pressure only, sir. No, Nana, capillary pressure is different. I told you capillary pressure is negative because of surface tension. That is different, and this is different. Sir, I have not understood how loose sand curve is drawn negative volume. You please go through this once again. What is the point I mentioned? In the case of loose sand, compression occurs. What is the meaning of compression? Right? Compression means reduction in volume or gain in volume. Reduction in volume. So reduction in volume means minus. Minus means reduction. Interlocking breaks suddenly means the strain is constant up to stress where interlocking breaks. Yes. So if shearing continues, then does loose soil will be acts as dense? Yes. So is volume, pore pressure, stress and void ratio depends on stress, shear strain? Yes. So here critical, what does it signify? At certain point, the dense and the loose are going to behave at a particular condition. That condition is going to be the critical condition. Behavioral changes means how? Means just now you see na dense sand behaves like a loose sand behaves like a dense sand, same thing. How much this chapter is remaining, sir? Lot is remaining, sir. Today's class is too much boring and a bit harsh to understand. Sometimes it happens, but you have to go through the notes once again because these topics are not that easy. So I am saying I refer 6 textbooks to make sure to understand you each and every point. Every textbook has a different points. Now, if you go through these notes and you can check any textbook or any material also, I have covered each and every point regarding to that. Tomorrow is a holiday. Tomorrow is a holiday. Eid Mubarak. So see, you go through this point, the results in positive pore water pressure. See for the second graph, this B, positive pore water pressure, loose sand, positive pore water pressure. What is the meaning of delta U pore water pressure? Plus means positive, positive means increases, increases, increases. But in the case of the denser sand, what happens is at first due to compression positive and then due to dilation negative. So at first due to compression positive and due to dilation pressure, pore water pressure becomes negative. So, but we can record the strain occurred at failure shear force. Yes, we can record the strain, but see the calculations are going to be different, Nana. I never thought I would get this chapter in my mind, even a little when I was preparing, but your explanation proved my thinking wrong and I'm very grateful. Yes, I'm grateful to you, my dear student, because I know it's a bit hard to understand the shear strength chapter at once. But if you understand, I'm telling you, this is a beautiful chapter. If you go through the notes, then you can understand the beauty of this chapter. If you study only, then only that will happen. Else it won't happen. Sir, why are you looking so exhausted? You were completely understanding everything. Yes, means when I discuss this type of topics, I know, but I'm seeing a lot of people are not attending, so that's the reason why. Well, let it be. But if the people are, means, somebody may have problems due to internet issues and all those things. I hope those people will go through the recorded videos. See, my point is, I always try to make sure whatever I say from my mouth, I want to make sure each and every student should be able to understand those. So that's the reason why I take more time to make you understand these things. Raise a hand option. Okay, I'm sorry, I did not raise the hand. Oh, sorry, sorry. Now, those who want to raise your hands, you can raise your hands. Yeah, I'll be sharing the PDF. Sir, in offline, you used to share many non-technical experience, but here you are not. Because here already time is going to be too much. I'm taking too much time for explanation. So if I go for the non-technical things also, your subject won't get complete. So I am not focusing over those. Remember, negative volume change means volume reduction. Negative volume change means, what is the meaning of volume reduction? Decrease in the volume. Decrease means minus only, right? Sir, please explain why the friction is less in place, though the cohesive forces are more. Please explain. Okay. See, the friction is different and cohesion is different, Nana. Friction is moving between the particles, whereas cohesion is attraction between the particles. That is different. Okay, fine. Yes. So now let's see the people who have raised their hands. A lot of people would be waiting. Mr. Shankar. Mr. Shankar, you can speak now. Mr. Shankar, you can speak now.
Sir, I have doubt in ESC previous questions.
ESC previous question. Which chapter?
Last chapter, sir. Last one.
Last chapter.
Yeah, I mean consolidation.
Consolidation.
Third, sir.
Which one?
23rd question.
Third question. What happened?
Sir, that last point, I'm not able to understand that last.
This is the question, right?
Yes, sir. The increase in. Oh no, sir. Just a minute.
Which question you are saying, Baba? Please tell me clearly.
Sorry, sir. It's in compaction.
In compaction.
Yes, sir.
Which question? 23, yeah?
Yes, sir.
Tell me.
And an increase in the organic content of clay, the third point, sir.
Cause increase in the optimum moisture content. I told you finer the soil, lesser the MDD, and see, coarser the soil, higher MDD and lower OMC, right?
Oh, yes, sir.
Fine soils will be having more OMC. If you increase the organic content, then the soil will be much more less or much more compressible. So I told you the clays with high plasticity or compressibility will be having a low MDD and high OMC. Yes or no? We just
Yes, sir.
have the type of soil. In that graph, what I mentioned is if the finer content increases, the graph would be falling down, which means OMC increases and MDD decreases.
Yeah, okay, okay.
Yeah.
Sir, one more question, sir.
In this chapter?
Yes, sir.
Yeah.
Sir, when is vibroflotation used, sir?
For sands. Vibroflotation technique is used for the compaction of sands.
Okay.
Yeah, okay.
Thank you, sir.
Next to Mr. Sachin. Mr. Sachin.
Hello, sir.
Yeah, Sachin, tell me.
Sir, ESC word questions, sir.
ESC?
For compaction chapter, sir.
Which question?
27 and 28. 27, sir.
Yes.
Sir, I got answer as 66%.
Yes.
But answer is 77%.
Compaction test for the maximum density for a certain soil give the results. And the specific gravity of the clay soil was 2.66. What was the degree of saturation for this one? So you can directly find out gamma D is equals to G gamma W by 1 plus E.
Plus E.
Find out the E value. What is the G E? 2.66 into 1 by 1.77 minus 1. 0.66 by 1.77 minus 1. So which is going to be 0.50. Then E into
Aye.
S is equals to W into G. So SR is equals to, what is the moisture content we got? 14.44. So 0.144 into G value 2.66 by 0.5. Yes, I got it as 0.768. 6.8%. Nearby is 77. What's the problem? Where you have done wrong? I think you might have done something wrong. You please check it out.
By taking the value of ohms. By taking the value of ohms, I am taking wrong.
Okay, fine. So you might get wrong over there. Okay, now you
Yes.
yeah.
28th.
This chapter only.
This chapter only 28th.
20th one. When the compaction energy increases, the compaction of soil increases. Hey, I have said that higher the compaction energy, higher the MDD, lower the OMC. Please go through the notes once.
Not this one, sir. 28th. Sir. Problem on 28th.
20, which you are saying? Gate or
20, 28. Yes,
28. Okay.
Yes.
28. Okay, fine. What happened over there? Maximum dry density. What is the degree of saturation of the soil? If this same question, Nana. Whatever.
I got answer as 98.4.
Again, okay, fine. Let me check. See, you have done something wrong in between. Now, let me check that again. E is equals to G gamma W by gamma D minus 1. 2.65 into. So let's take it as see, as they have given very nearest values. So you go with the 9.81 only by gamma D. What is gamma D? 18 minus 1. See, from the previous years now, all the fellows, whatever the paper setters are, they are giving the questions in such a way. Actually, there was a rule in the ESC that you cannot give a questions without using that can use with the calculators. But they are giving these questions now. So what is the value of 0.16 into 2.65 by answer? So after solving this is going to be 0.954, which means 95.44. Yes, answer is going to be B, right? What is the answer they have given?
Sir, if they given in the.
What's the problem you have?
Yes, sir.
What is that? I'm getting a lot of sound.
Wait, sir. Moment.
It's already.
Sir, in this case, we can use theoretically
you use theoretical.
Theoretically,
That's see, when you do that test, that is going to be not theoretical, right? If it is a theoretical, the degree of saturation is 100%, right? Then if you use theoretical, degree of saturation is 100%. Okay, so that's it.
Okay, sir. Thank you.
Yeah. Miss Nikita.
Good afternoon, sir.
Good afternoon, Nikita.
So my doubt is regarding previous gate 15th question, sir, 11th chapter.
11th chapter.
15th. Yes, sir.
Now what happened?
In that E is not given, sir.
Using the of clay layer derived from the above question, they have mentioned the above question, right? You see the question below. That's a code 14th and 15th are linked questions. From the given data, you can find out the E value. You have G value, right? Specific gravity is at 2.7.
Yes, sir.
Water content is there.
Okay, okay.
Saturated soil is there. Degree of saturation 100%. Seva E into SR is equals to W into G. You can find out void ratio there.
Yes, sir. Yeah.
Okay,
And
fine.
20 questions, sir. Same chapter.
Question number 20. Yes, tell me.
I'm not able to get the answer, sir.
Okay. Water tank is to be constructed on a soil deposit shown in the figure. A circular footing of higher 3 meters and depth of embedment 1 meter has been designed to support the tank. The total vertical load to be taken by the footing is 1500. Assuming the unit weight of the water is 10 and the load is dispersed, the expected primary settlement of the tank due to primary consolidations layer. See, they have given the 3 meter of the circular load. Yes. And
Yes, sir.
the footing is located at a depth of 1 meter. That's just 1 meter only. Okay. So first of all, in the case of clay, what is the thickness? The entire thickness is going to be under clay. H is there.
10 meters.
Given CC is there. E naught is there. And what they're asking is what they're asking? Settlement only, right?
Settlement. Yes, sir.
Yeah, fine. CC by 1 plus E naught into H into log base 10 sigma naught dash plus delta sigma dash by sigma naught dash. Everything CC is there, E naught is there, H is there. Now you have to find out sigma naught dash. Sigma naught dash means at the center of the clay layer R naught.
Yes, sir. 15.
So now which means gamma of a sand into 2 meters plus this is going to be a sand, but this is going to be a sand. Gamma.
Submerged gamma dash.
So into 6 meters plus gamma dash of clay into 5 meters.
5
Right?
meters.
So
Yes, sir.
52 plus 8. Let's take gamma W.
118.
Given is gamma W 9.81 given?
No, sir.
Okay,
I
fine.
take it as 10.
Okay, fine. 10 plus again saturated of the normally conserved rate is also going to be same. So 8 into 5. Okay. Which means 8 is 48, 6 48, 88 plus 30.
8 plus
What
30.
comes?
118.
118.
118.
Now coming to the sigma naught dash, sorry, delta sigma dash, that is going to be q by pi by 4 into b plus z whole square r naught.
Yes, sir.
This is for circle.
1500 bar.
Point the circle. What is the z value you need to take? The z value is going to be like here 1 meter below. This is 1 meter plus 6 plus 5. 12 meters should be there. Delta sigma dash, whatever this z is there, na? The z is going to be 12. Have you got 12?
No, sir. I take it as area of footing as pi by 4 diameter square.
That's where you got the number. Okay. That is
Means Z means from the top one, from below 1 meter, we need to take it as Z, sir.
yeah, below 1 meter we have to take. So in the sand layer 1 meter, silty sand, in sand 6, 1 plus 6, 5, 7, and in clay 5 meters, 6, 7 plus 5, 12 meters. Okay. If you solve that, then you can get it.
B means what, sir?
Huh?
B.
B means dia. In the case of the square, B is width.
Okay.
In the case of circle, B is dia.
Okay, sir.
Okay.
And 21 questions. Next question.
I have been explained this question, right? Didn't I? What's there in it? Tell me.
Like I got the compaction as 60%, sir. Consolidation, degree of consolidation. So that I take TV as 0.286.
Why you are taking TV value as 0.286? Have you got the TV value 0.60%? Sorry, 0.286?
Yes, sir.
How?
30 by 16.
30 by 60.
50, sorry.
Arey Baba, see, understand the question clearly. Understand the question clearly. First thing. Here, 20 meter thick clay layer is there. Sand which between silty sand and gravelly sand. So then the drainage path is be 10 meters.
Double drainage.
The soil layer experienced 30 mm in 2 years, which means in 2 years of time, what is the settlement? 30 mm.
30 mm.
If the coefficient of consolidation is CV, the deposit will experience a total of 50 mm settlement in next which years? They are not asking ultimate settlement. So for the next years, if I want to get total of 50 mm, then what is the time? They are asking this one. Okay. Understood now? They did
Okay.
the ultimate settlement to you.
Okay.
So you need to find out TV. What is TV? CV into T by D.
Divided by D squared.
So for the
Yes.
first step, CV into T1. So now you have CV, and from that CV, 0.003 into 10 to the power of -4, which is
Meters.
what square into first 2 years. How much settlement is there? First 2 years, T1
30 mm.
into 2 into 365 days into 24 hours into 60 into 60 by 10 square. So have you got TV as 0.189?
No, sir.
There comes. See, you took this S2 as ultimate settlement. No, they
Yes.
are asking that if it is 50, then what is the time? Now you find out the value. You observe. Yes.
Okay, sir.
And TV2 by TV1 is equals to T2 by T1.
Divide T1.
Yeah. Now you need to find out the T1 also. So sorry, TV2 also. So you can find it out from these equations. You can find it out. Okay, don't worry about that.
Okay, sir.
It's already been 137.
Sir, in ESC 56th question, sir. Same chapter.
Yes, see, same chapter.
ESC. Same chapter.
Yes, tell me. Tell me what happened. Hello?
Sir, in that Q, SI, sir, in that he has immediate settlement, sir.
Hmm. They
So
are going
that
to put
Q will
inside
be
the
600.
Yes.
So that I got answer is different, sir. 24 something, around 24 I got, sir. But here answer is given as around 22.5 or
Let
25, I think.
me check. Q by E into B into 1 minus the square into I. Okay. Q how much?
600.
By E. 2
2.
megapascal. So which means 2 into 10
2
to
kilo.
the 3 into B. Width is going to be 1 into 1 minus 1 minus 0.5
Square.
into 0.
0.9.
Okay, fine. 600. So which is going to be 10 to the 0.6, 0.3 into 1 into 0.95 into 1 minus 0.5 square, which is going to be 0.75. 0.3 into 0.75 into 0.95. Yes, what is the answer they have? After solving, it is going to be 0.2137.
1.5. Yes, sir. 2.
The answer would be near value 22.5, right? The nearest value is going to be
Okay, nearby value.
see, in ESC they won't give the exact,
Okay, okay.
give the nearest values. Okay,
Okay, sir. Okay, sir.
nice. Yes,
Thank you, sir.
yeah, thank you. Next, Miss Mona. Miss Mona, you please speak up.
Sir, is it audible?
Yeah, Mr. Tell me
Sir, I have a doubt in calculation, sir.
which way.
So, how to do the tan inverse square in a virtual calculator, sir?
Tan inverse square, see that you can do the tan inverse, right? So first you need to go to the inverse, then tan and the value.
First, I have to do the tan inverse, then
Yes.
where
No,
it.
no. Generally, in the normal calculator, we do tan inverse of first you tan inverse and then you give the value. In
Yes,
the
sir.
case of the virtual calculator, first you need to keep the value. First of all, if you want to go for tan inverse of 0.5, first you keep 0.5, then tan inverse.
10 power 0.5 and then tan inverse, sir.
Yes.
Okay, sir. Thank you. That's the doubt, sir.
Yeah. Mr. Mohit. Mr. Mohit.
Good afternoon, sir.
Good afternoon, Mohit. Tell me.
Sir, 11th chapter, question number 41 of EAC.
Hmm?
11th chapter, consolidation, question number 41 of EAC.
Okay. This one.
Yes, 41.
Considerable loss of shear strength due to shock or disturbance.
Sir, it should be organic soil, no? But answer is under consolidated.
Alright. Why it is organic soil? Considerable loss of shear strength due to shock or disturbance is exhibited by. Yes. Under consolidated clays. Why, sir? See, what is the meaning of normal consolidated clay?
Present stress would be more than the
And
past.
soil got already consolidated, right?
Yeah.
And OCC also, soil also got consolidated. But what is meant by under consolidated?
Max stress is still not known.
During consolidation, yes or no?
Yes. Under
During
construction.
consolidation means the pore pressure is dissipating, yes or no?
Yes.
Are Baba, during that, if you cause any disturbance, then again the excess pressure will decrease or increase.
What, sir?
Already clay is under consolidation, okay?
Yes.
Now you apply suddenly a shock or a disturbance.
Yes.
And again, due to the disturbance, excess pore water pressure will increase or decrease?
It will increase.
When excess pore water pressure increases, what happens to strength? Decreases or not?
Decreases.
That's it.
But in the option there is organic soil also, but we don't know.
Organic soil, see, we don't discuss about the strength of the organic soils at all. We don't discuss about all those things, okay?
Okay.
Yeah.
Okay, thank you.
Yes. Miss Aparna? Miss Aparna, please speak out.
Good afternoon, sir.
Good afternoon, Aparna.
My doubt is regarding previous IS, sir.
Previous IS?
Consolidation
Yeah, which question?
58.
Tell me.
So in that question, I got the answer as 5.39 centimeters.
The nearest value is 6. The nearest value is 6 now. See, for the ESC, as they don't provide the calculator, they will give you the approximate values. Understood?
Okay, sir. But
Yeah.
the answer I got, whether it is correct or not.
That is correct only. That's correct only. Let me check once. The time taken to construct a building was from 1992 to 1993. So 1 year. In September 1996, the average settlement was found to be 5.16. As they have given the average time period, you have to start with the average time period. So from 1992.5, which means that's going to be 3.5 years, right?
3 points. Yes, sir. 3.75.
I1 3.5 years, and settlement was of 5.16 centimeters. And if the ultimate settlement is going to be 25 centimeters, then the settlement in January 1997 would have been. See, 1997 means so 1996 and 1997, which means 4.5 years. Yes or no? Here
Yes,
the
sir.
simple logic is, you see, U1 is going to be 5.16 by 25 into 100. Yes or no? Don't calculate. Don't calculate. But you know that 5 by 25 means 1 by 4, 25. Just more than 25%. Yes or no?
Yes, sir.
And now, within 1 year, 3.5 to 4 years, do you think, you know that as the time increases, the degree of consolidation rate is going to be less? Yes or no?
Yes.
So by the end of the 97, directly U value would be less than 60% only. That's the logic. So then you can use directly T direct proportional to S square. If you use that, so now 4.5 by 3.5 square, it is nothing but S2 by 5.16. Yes. So now you can find out root of 4.5 by 3.5 square root into 5.16. You can get as a 5.85. The answer is going to be 5.85 centimeters. Okay?
Okay, sir.
Yeah. Understood or not?
Yes, sir.
Yeah.
49.
Of this chapter?
Yes, sir.
Question lesson. Which point you need to find out?
Second and third.
Clay's compact and dry of optimum compresses more rapidly. Clay's compacted weight of optimum consolidates more under low stress ranges. So there is a compressibility also. Point actually, the clays which is on the dry of optimum, it undergoes more compression because the structure is going to be flocculated structure or not. Yes or no?
Yes, sir.
No, dry of optimum compress more rapidly. No, there is a one point for that. Place compacted dry of optimum compresses more rapidly. No, place compacted dry of optimum compresses less rapidly. Less, they can compress less. And clay's compacted wet of optimum consolidate more under low stress range. Because on the wet side, the water content is going to be more or not.
Yes, sir.
When you consolidate, more water will go out, more consolidation will take off. C is first and third one are correct.
But option given as A, sir.
All are correct.
Yes, sir.
Okay, let's check that once. Right. I'll check it and I'll let you know tomorrow, okay? I have a small doubt.
So last one, 35.
Yes. Last one?
35.
35.
Yes, sir.
Estimation of settlement of foundation on sandy soils can be done by SPT. SPT means standard penetration test, Nana. That we will be discussing the last chapter in soil exploration. There we will discuss. Okay.
Okay, sir.
Yeah. So for today, I'm stopping this. So it's already been 1:50. And if you have still any doubts, you please go through the notes once, and then we'll see the things tomorrow, day after tomorrow. Tomorrow is a holiday. So I'm stopping the sharing now. Bye.